Cool, well let's get rolling, and thanks everybody for coming. Looks like we've got a lot of people here today, so that's awesome. And hopefully we'll cover lots of interesting things and have some fun here. So we'll just get started and see where we get to and kind of talk about the plan. So just a tiny bit about me. My name is Adam Breindel. I do a lot of consulting and training with Spark and big data engineering and deep learning and various things like that. My first job I forgot my hat. My first full-time job in technology about 20 years ago was actually down the road in Providence, Rhode Island with a startup called Nestor, which was doing neural network stuff back in the 90s when none of that stuff worked right. They had what we would now call a shallow radial basis function network, although at the time it was a patented network. People actually did that back then. They patented their neural network patterns. And they built some interesting things with it, and it kind of half worked, but you know, this session isn't about the history of that startup. It doesn't exist anymore, but it was fun. So since then, I've been doing lots of other fun things, and the cool thing nowadays is the tooling has gotten so much better, of course. Obviously all the technology is better. And everything's open source. So now if we want to solve some hard problem, you get like 85% of the way there just by finding some appropriate project and downloading it, and you basically spend the rest of the time just doing that last 10 or 20% of the work, which hopefully is the most interesting stuff. We don't have to build all of the infrastructure by hand like in the old days. And that's turned out to be true not just for machine learning and data science stuff, but just big data analytics in general. The stuff that you get out of the box with something like Spark now are things that we literally, like at Wells Fargo, spent a year, 2 years building to get just a tiny subset of that to run. And now it's like you just download it and it works. It probably works better than what we built because it's actually tested by thousands of people. So anyway, it's a great time to be doing this, and we'll see where we can go with that. My contact information is here. You're welcome to email me after the session, like for example, if you have any questions or if you just wanted to see other code samples. A lot of times people say, well, that pretty much made sense, but do you have an example of doing X? Like, I can't find that or whatever. I probably have a sample of code somewhere for almost anything that you might want to do, or I can figure out how to figure it out. I do a lot of work with Databricks. We'll be using their tool today. So I don't work for Databricks, but I do some work with them, so I have some access to the engineers there that work on Spark and stuff like that. So we can usually track down problems if weird things happen, and I'm happy to help. So these are super high level of objectives for what we're going to do today, and then I'll kind of drill down. So we want to use Spark to process data set features. Specifically what I mean is feature engineering that is not so obvious with the out-of-the-box Spark tools. So the main theme of this whole session, and just to also let everyone know in case it wasn't clear from the schedule, this is kind of a two-part thing. We've got the morning session and the afternoon, and it's all one long session. So you're welcome to come to both. If you can only come to one, that's fine. If you come to one and decide an hour into it that it's not for you and you go running for the door, I don't take it personally. So just you're welcome to kind of mix and match whatever works for your schedule. But the general theme is trying to do things that are a little bit trickier than what's right out of the box with Spark. So we'll look at some. Oh, hey, how's it going?
Good seeing you.
Yeah, same. So.
No,
I know. So this is one of our great MCs, but I wasn't sure exactly. I thought maybe there was an emergency somewhere and I should just get started.
Yeah, sure. So, hi everyone. Welcome. First session of the day. And we are excited to have you all here. So how many of you have ever been to any other ODSC conference or meetup or event? 3, 4. Okay, so pretty new crowd. Great. So ODSC. We are a community that tries to bring data science around the world and make it accessible to everyone. So we have been everywhere. Adam has been with us half of the world too. And we are very, very happy that we have Adam. Adam is the first time that Adam accepted to come to East Coast to Boston. Adam is one of the best instructors in the world of big data, and especially Spark in West Coast. As you know, Databricks is one of the big players in the world of Spark in the West Coast, and Adam is among the very few independents that know it really inside out. So we had the privilege to host his sessions a few times in West Coast, but we are very, very, very happy that he accepted to come to Boston to host this session. So thank you very much, Adam.
Awesome. Thank you for the intro. Cool. So yeah, I hope he doesn't have too many of those to pack in the first 15 minutes of the day. It's a big building here. Cool. So yeah, we're going to do all these things with a focus on trying to, and I'll find out kind of where everyone's background is in a minute, and we can adjust the level of the presentation a little bit. But the general idea is that you probably have used Spark somewhat before, and you've probably seen some examples or tutorials or documentation about all the stuff that's like just built into Spark before, and hopefully that more or less makes sense. And what we're hoping to do here is figure out how to go a little bit beyond that. So you want to do something which is a normal data science task, but is not exposed in the current Spark API. So we want to see how to do that. Or you want to extend the Spark API in kind of a proper way, like a way that you can share with other people and reuse. So that's kind of the theme of the whole project here. So we'll do some feature processing. We'll assemble some pipelines. We'll talk about strengths, patterns, and limitations of Spark ML. So that's actually a really useful piece, is we want to figure out what is Spark great for, what is it not great for, we should use other stuff, what could it be good for with some modifications. So kind of these interesting things around the edges, like when you get out of the obvious sweet spot where all the demos are, what things make sense and what things should we either, well, I don't know if stay away from, but what things should we kind of approach a different way. So we've got, in the morning part, I've got a lot of, maybe not demos, it's all going to be hands-on. So you'll have in a minute notebooks where you'll be running the code alongside with me, and you can experiment with it. So when I say demos, you don't have to code a lot of stuff from scratch, but you can modify the code, and it'll all be interactive. In the afternoon, we'll have some more lab-type stuff where we want to talk about creating our own pieces that fit into the Spark API. There'll be lots of explanations and there's solutions and stuff, so you won't get stuck and you won't have to stare at a blank screen with no code. Don't worry about that. But there'll be a little bit of a chance to actually try and write a little bit of code and experiment and get these things to work. So we'll have a bunch of those this afternoon. I don't know if anybody here has been to any of the, as you heard in the introduction, I've done a couple of these sessions before with ODSC. I don't know if anyone here has been to those. But I've updated for this one a little bit. Spark is updated, and I also added, I stripped out a couple stuff that I thought was too easy or boring, and I added something near the end that I thought was a little more exciting for this session, so it should be, I hope, even better. Things that we're not really going to do today, so we're not going to talk about core Spark job execution or cluster configuration. I'm happy to answer questions about that, and it's really important in terms of getting your jobs to run right, but the problem is that's like an entire, at least half a day by itself, is how does Spark actually run these jobs? So that's, if you're interested in that, maybe we can figure out some other time to work on that, but we won't get a chance to do too much today. We're not going to talk about kind of basics of data science or predictive modeling, so I'm figuring people who are coming here probably either already know that or they're probably learning that from some other location, so I won't spend a lot of time on exactly too much of how that works. I won't list out or demo like 50 algorithms that are in Spark for a couple reasons. Well, it's time consuming, all that stuff is in the docs anyway, and if you're in data science, you probably also use tools like, say, R, and these other tools have more algorithms than Spark does anyway, so it's not like I'm going to show you a list of algorithms in Spark and you're going to say, wow, that's amazing. So we're going to kind of focus in on some specific ones. And we probably won't talk about the math or the CS too much. Maybe at the very end we'll talk a little bit about that, because we will try and do a new algorithm. We'll talk about using gradient descent for parallelization and stuff like that, maybe at the very end. So one of the things that makes these sessions exciting is that I have no idea who's coming until you guys come, and that's kind of a feature, not a bug, right? You sign up to come to the conference, and then you can come to whatever session you want, but I don't know who's here. So let's do a little informal survey, just so I have an idea of what your experience is in terms of Spark, and then I can adjust things so that it's hopefully as useful to you as possible. So raise your hand if this is like the first time you're ever using Spark today. Okay, so maybe like 20%, something like that. Raise your hand if you've used Spark a little bit, like run a few queries or commands, but you've never really built anything serious with it. Okay, cool. So maybe about half. And then if you've been working with Spark for a few months, so one person. And then like if you're working with Spark in your job for like 6 months or more, so you're pretty much like this is your normal job. One person. Okay, interesting. Okay, cool. So so the level on Spark is a little bit more basic. That's cool. Because there's so many people who are either totally new or barely used Spark before, like together it looked like about 90% of the people here, I'm going to skew things down a little bit. And what I'm hoping is that for a couple of people who are more veterans here, that there will also hopefully be valuable content for you too. I don't want you to be bored. So I will try and kind of edit things so we do include some really interesting stuff. And also feel free to interrupt me anytime with questions, stuff like that. So if you're, you said you've been using Spark a ton. If you're sitting here and you're like, okay, I get this, but what about X? Feel free to just ask. And if it really goes off the rails, I'll talk about it. And we'll bring it back together. But it's the session's for you, not for me. So definitely tell me anytime if we want to talk about something specific. This is the approximate schedule. We'll get set up here. We'll have some intro stuff. We'll get everybody running on Databricks, get all the notebooks and stuff imported, kind of the lab materials, so everybody's got everything running. Then we're going to talk about Spark ML patterns. So that's something that we'll definitely emphasize more since people are kind of new to Spark. So how does Spark structure the API and why? It's actually really simple. But it is maybe a little bit not what you're used to. And once we kind of see how that works, then hopefully everything will start to click together. Then we have a couple of longer notebook kind of interactive labs on feature engineering, natural language processing, classification, and clustering stuff. So the problems there in terms of data science, we're not doing anything super amazing that's going to change the world. What we want to do is sort of see how to use Spark, how to get it to work, and then also how to deal with some of the trickier situations that are not just Google the API and punch it in. Then in the afternoon session, we'll talk a little bit about cross-validation with sklearn. That might be something that I drop if we're short on time. That's basically an integration between scikit-learn and Spark. And it's useful for some things, but it's not a solution to everything. So we'll see where we get with that. And then the big part of the afternoon, and this is to be fair and kind of give fair warning, this is going to be a little bit challenging for if you're new to Spark or new to, if you haven't used Scala before. It might be a tiny bit challenging. But hopefully it will be valuable, and that's how to extend Spark. So you have a feature processing task you want to do. Maybe it's something really common that doesn't happen to be in Spark. For example, imputing data where there's missing or bogus values. That's like 101 of data science. There's actually an API in Spark for that that's going to be in 2.2, but it's not out yet, right? So this gives you an idea. So Spark's been around 9 years. There's no built-in data imputer piece that fits into the API. So we'll talk about, okay, how would we code that? And then once we had it running, how would we wrap it up so that it looks like the other pieces of Spark API, so that anybody else in the world that uses Spark can use it, other people on the team can use it. So that's what I mean about custom feature processing. And we're not going to try and do really hard problems with that. We're focusing on integration, like how do you do it the Spark way and why? Custom algorithms. So if you have an algorithm that is not in Spark, but you'd like to add it to Spark, or maybe whether it's just something that was published in a paper, or it's in R but not in Spark, or maybe it's something specific to your business domain, how do you do that? And then the last piece there, we'll look at a couple ways to do that. So we'll focus on kind of the integration part, and then we'll look at how to use Spark's optimizers. So using gradient descent to add an algorithm. And then the last section is deploying and operationalizing models. So this is something that it causes a lot of confusion, not because it's super complicated, but just because Spark has so much hype around it. I mean, Spark is a great tool, and I love it, right? But when things get a lot of hype, the hype starts to drown out a lot of the detail. And so for example, Spark is great for doing certain machine learning tasks, but certain things really, really are a little bit tricky to do. Like the standard thing is I've built this awesome model, and my company says, cool, I need to hook it into my architecture via a web service, right? So the classic thing is we've got this model, and now I'm going to get a web service call from some random other part of the business, and they're going to send me a vector, and I need to predict. How do I do that with Spark? Well, there is no easy way to do that with Spark. You can get it to work, but it won't work well. But there are ways around that. So I want to talk about, okay, what's the problem? What's the solution? And I'll give you, links to stuff like that. We'll talk about understanding why. We'll probably also finish a little bit early this afternoon. Unfortunately, I have a flight I've got to catch tonight. So we'll probably, although the afternoon session says it goes till 6, we'll probably wrap up closer to 5:15. So, okay, so that's kind of the plan here. In terms of resources, so there is a Google Drive folder at this top URL, so tinyurl.com/ODSC-Spark. And that has a PDF with the slides. That's the slides I'm currently showing, which we're only going to use for part of the day, but that way you have a copy. There's also a couple other things in there that you won't need right now, but I figured you might want to play with them in the future, so why not give them to you? So I think I have a compiled version of an Intel deep learning library that we're probably not going to use today, but if you wanted to run that notebook, you could use that library. I also put in there, what else did I put in there? A copy of the labs. You don't need to download the labs from this folder. We're going to kind of sideload the labs directly from another server, which will make life a little easier and not strain the Wi-Fi. But they are there in case you want to download them in the future. And all these materials, although they have my copyright on some of them, and some of them that don't have my copyright are published by Databricks, they're all Creative Commons. Well, they're not. The Databricks ones are Creative Commons in the sense that you can use them, you just can't sell them. And my stuff, you're welcome to, you're informally welcome to do whatever you want with it as long as you don't sell it also. So you can reuse those for meetups or brown bags at your company or whatever else you might want to do. So that's why I put all of that material in there. And that folder looks something like this, if I can get the screens to work right here. So that folder looks like this. Like I said, you don't need, this is the lab material. You don't need that right now. This is a library for the deep learning. You don't need that right now either. This is the slides, which you might want, because once you have this, you got the links and stuff in there. So that's all we've got going on there. And the next thing we want to do is set up a Databricks CE account. So I'll talk to you about that a tiny bit, and then while you're getting that set up, I'll kind of explain some things. So I made a shortcut, tinyurl.com/Databricks-CE. And that will take you to this sign-up form. So Databricks CE is it's a permanently free, like not time-limited or anything, miniature version of the Databricks environment, which is a kind of a simple interactive environment for working with Spark, so you don't have to run it on your local machine. You can think of it as it's a little bit like Jupyter, IPython notebooks. Has everybody here used those at some point? Probably, yeah. It's very much like that. The code is not the same, but it's similar experience, right? So it's a nice interactive way to play with stuff. You don't have to compile code. You don't have to deploy servers. And so we'll use that for most of the day. So let me know if you have any challenges getting the Databricks account set up. It's usually pretty much instantaneous. You get a confirmation email. You can use pretty much any email you want, including a bogus one. As long as you can receive email from it, it's fine. So you don't have to use your official work email or anything like that if you don't want to. Cool, so hopefully that's working. Again, let me know if you run into any problems, which we should be able to troubleshoot that. You want to use Firefox or Chrome. So the Microsoft browsers don't work perfectly, and Safari is particularly devilish because Safari mostly works. So it seems like it works until it just suddenly doesn't. So Firefox or Chrome will work well. And then at the bottom there's this URL. That's where we're gonna kind of sideload all of the labs and stuff from there. So you can either type that in a minute, or you can just copy that. We're going to use that in a second to get our labs set up. So the idea is that once you've got your account and you log in, you should get a screen that looks something like this. Almost exactly like that, actually. And then I'll walk you through the slides for this. Then I'll import the data live in my account so you can see both, kind of see it live. So then the next thing we're going to do to import this is we're going to start with the left-hand nav and click the workspace button here. And that will show this kind of menu column right here. We'll click the drop-down affordance next to the word workspace, and we're going to go import. And that will bring up this dialog box over here on the right, the one that says import item. So I'll go through this twice. So again, you don't have to be like trying to keep up with exactly what I'm doing. In this import item, we're going to click URL. We're going to punch in the URL from the previous page. Luckily, the one we're using today is not as messy as this, so it's easier to type. Or you can just copy paste it. That works too. Click import, and that's pretty much all we need to do to get set up. Then we're going to go and create a Spark cluster. And to start that activity, we're going to use the clusters button on the left-hand nav, and then the blue create cluster button. You can name your cluster whatever you want. And for the Spark version, we're going to use this version that's listed here, Spark 2.1.0-DB3, Scala 2.11. I'll explain all that in a minute, but that's the version. This is a big old drop-down list of Spark versions. Just pick that one and click Create Cluster, and at that point, you're pretty much set. And then we'll create a test notebook. So let me bail out of the slides here for a second and demo this for real. So what I'm going to do is come over to the appropriate browser here. Let's make this bigger. And we'll zoom this in a little bit. That looks pretty good. Okay, so this is what it looks like when I log in. And then over here, we've got this left-hand nav. I'm going to go Workspace. And then I have all kinds of junk in mine because I've been using this for other stuff. But when you first start out, it will look just something like this. And then I'm going to go under Workspace. I'm going to go Import. Then I'm going to click the URL radio button, and here's where I'm going to put that URL from the slides, and I'm going to be lazy and copy it. So I'm going to come back to here. I'm going to literally just copy this. If you downloaded the PDF, you could copy it out of there. So it looks like that. And then I'm going to go import. And if you notice on the left here, it just popped up a folder that says ODSC East 2017, and in there is all kinds of stuff. So these are all the materials we have for today. We probably won't use every single one of these notebooks, but when I was editing this down, I always felt like, why take away something? Like I can always give it to you, and we don't use it. You might want to play with it later. So this is all of the materials, and it's as easy as that to get set up. The data sets we're going to be using here are all pre-mounted kind of on the back end, so you don't have to do anything to get access to the data. So before we go any further with this, just to give like a quick 20-second rundown of what's going on with Databricks. This is all about open source, so I don't want to be like giving a commercial for Databricks, not because they're not a great product, but because that's just not what we're here for today. But I want to explain a tiny bit about what the machinery is here, just so we know what we're working with. So there's a couple pieces. We've got this nice GUI, which is obviously like a web app. When we go into this thing that looks like a file system, right? There's a folder. This looks like a bunch of files. In my particular environment, I have lots of other folders and files. And it looks like I have almost like a home directory here, which I do. So what is that? What that is a bunch of data sitting in Amazon S3. And Databricks has a wrapper over that called DBFS, or Databricks File System, that just exposes S3 buckets as a Unix-type file system. It's a little bit like the EMRFS tool that's part of Amazon, where if you're using like Amazon Elastic MapReduce for Spark or Hadoop, you can use EMRFS to talk to S3 like it's a file system. So it's very much like that. That's pretty much the essence of it. And so it's handy if your company has like, huge data sets in S3, you don't want to physically move those to work on them. It allows you to just essentially mount them by reference. You go, I want the path /foo to point to this giant bucket of terabytes of data, and it just works. So that's the idea there. And here we're just putting our own notebooks and files in there. In terms of the Spark clusters that we're going to be using, so I'll go and make one of those here. So in Databricks Community Edition, Databricks is paying for all of the EC2 instances that back these clusters, which is very nice, but the trade-off is like the clusters we're going to get are very tiny. In fact, they're not even really clusters. They're kind of pretend clusters. So I'm going to come in here and I'll say demo. And I'm going to pick, let's see, so 2.1.1 actually just came out officially this morning. We're not going to use that because I don't want to use something that just came out this morning. I mean, I'm sure it's fine, but I just would rather not take the risk. 2.2, by the way, should be out like within a week or two. It's already on its second release candidate, so we'll talk about that a little bit. But for now, we'll go with 2.1.0 here. And I'm going to go create cluster. So the idea is that if you're running a commercial version of Databricks, you can use this to manage many different Spark clusters using different instance types, different amounts of CPU, different amounts of RAM, and do all kinds of interesting stuff. Instead of having to work directly with, say, Amazon CloudFormation, or having to have your operations folks do this stuff with VMs directly. In the Community Edition, what we're really working in is a tiny container that is stacked together with other containers on a single EC2 instance. So our cluster here is really just one local mode instance of Spark. Local mode means that it's a Spark driver and not really any distributed pieces of Spark, but it pretends to be, but it's all packaged together. We have 6 gigs of RAM, so we're not doing huge data computation here, and 0.88 vCores in terms of CPU. It's presented as 8 cores, but it's not really 8 cores. It's really 8 threads that together have access to less than 1 core. So the point is that in terms of horsepower, you're not going to be doing like big data on this free edition, and we're not going to be doing that today. But the way we interact with Spark by design is almost identical, whether we're working in local mode on our laptop, or in local mode here in the cloud, or on a giant distributed cluster. Like that's the whole purpose of Spark, is that you don't need to worry about that. The framework is designed to scale out. So there's a couple little tiny differences, but generally speaking, it will work the same as if we had a big cluster. So that's what's going on here. And you can see there's a little kind of readout here. I don't know if we'll need to actually use too much of the stuff under the cluster screen here, so I'm not going to spend too much time on it. And okay, so we're all set up over here, so let's flip back to the slides. So we've done all of this stuff. Oh yeah, while we're here, why don't we create a new notebook just so I can demo how that works. So I'm going to come under here, and you can actually create these things anywhere in the file system, but just to keep it really simple, I'm going to do my stuff at the very top of the file system under Workspace. And I'm going to go Create Notebook and create a new blank demo notebook. So I'll call this thing Test. Under Language, you can pick the default language for the notebook. So you can mix languages in the same notebook using magic tags that are similar to IPython or Jupyter magic tags. But whatever we pick here will be the default language for the notebook. So let's say I want to do a Python notebook. And then I can pick which cluster I want to attach this to. The notebooks are not married to a cluster, so if you were doing this in some production environment, you might code or test on some small cluster, and then set up that notebook, maybe then detach it and run it on like a large QA cluster, and then maybe set it up as a scheduled job against an even bigger cluster. And we can do all that, but this is where we're going to start, is on this little demo cluster. So it says attached, and now we can get into some serious data engineering, like maybe adding 1 + 1, just to make sure everything's alive here. So we can punch in code, and it's if you use Jupyter, it's a similar kind of environment, right? So we can mix Markdown in here if we want. If I go, I can. The way I'm executing these cells, so notice it says Shift Enter to run. So that's like the main shortcut. If you don't know any other shortcut, that's the one to get started. If you want to learn other shortcuts, if you click the little keyboard icon, there's a huge list of all the other shortcuts that you can use. Most of these things you can do with a mouse or a keyboard. Like Jupyter, it has a modal interaction. In other words, it's kind of edit mode and command mode. So right now I'm kind of in command mode where I'm moving around the cells, and then if I hit enter, I go into edit mode. So I can do all of that stuff. And so you may be wondering, well, hey, if my company is not using Databricks, or for whatever reason, like, is there any way I can get any value out of this? So we can take this code and we can export it. So if you go under File, Export, there are a lot of ways to get this out. The most elegant way in terms of being easy and pretty is the least flexible. That's DBC Archive. It bundles an entire subtree of folders and notebooks together, including the graphics that you might generate, everything else. But it puts it into this kind of weird JSON proprietary format that you can't really use anywhere else. Luckily, we can also go export as source file, which will dump out all the source code, and everything I put in here that's not source code, like for example this Markdown, will show up as a comment. You can also export as an IPyNB, like IPython notebook. And then lastly, you can export as static HTML, which is handy. Let's say you do some processing, you generate some cool visualizations, and you want to present them or send them around, and you don't want the other folks getting this to have to worry about Spark or Databricks or anything. You can generate an HTML file that looks just like this. It's kind of like the HTML export from IPython, except it actually works. Like it preserves everything, and so it just is not interactive. So that's how you can use this to experiment or try stuff on here, but then also bring it into your own environment. Cool, let's see. So we talked a tiny bit about this here, about Databricks CE, so that's kind of enough about that probably for now. A tiny bit about the data. So the main point here is that the data we're using in these stuff here today is not meant to necessarily be representative of the real world data. So that's pretty much the point of this slide. So don't worry about the fact that these data sets may be smaller than real data sets because we have limited resources. They may have fewer predictors than real data sets. They're relatively clean. We can talk about how to deal with other things, but they are sufficient for what we're trying to do here today. So let me dive into kind of what is Spark, especially because we have so many people that are pretty new to Spark. It'll be useful to talk about that a tiny bit. So Spark is fundamentally a distributed compute engine. That's the essence of it. That's how it's different from, say, databases or a lot of other kinds of systems that may seem like they have some of the same capabilities, is that fundamentally Spark is about doing compute. So for example, Spark does not own any of its own storage. Right? If you use like a database, it is very particular about how it stores things on disk, and you get performance benefits from that, but it's coupled together with some kind of storage. So Spark is designed to kind of be able to do ad hoc or on-demand data analysis or processing, because it can attach to almost any sort of data in almost any location. So you can attach simultaneously to data that's in a relational database, in S3, in HDFS, in lots of different formats. It could be Parquet, Avro, CSV, streaming data. You can treat all these things as tables and like join them on demand. So it's very flexible, but it doesn't own the data. So there's fundamentally some limitations, right? So the things, if you're reading plain text data from some faraway file, some faraway location, what you can do with that's going to be a little limited compared to if you had stuff on local disk laid out in a structure that you own. The model is data parallel. So the idea of data parallel architecture is that we have some large data set. We break it up into a bunch of pieces. These pieces are called partitions. And we run the same compute over lots of different pieces of the data, potentially in lots of different places. So that's what we mean by data parallel. So that gets particularly interesting when we talk about extending or creating like machine learning algorithms, because a lot of the reference implementations of algorithms or the way the algorithm is published in a research paper or a textbook assumes that everything is kind of in a local Turing machine kind of model where you go step by step. and parallelizing these things can be non-trivial. With Spark, the goal is that the system should scale out linearly. And so far it does into the tens of thousands of nodes. So that means that not only do we need to come up with some way to do things in parallel, but it needs to be pretty efficient, right? We can't take some shortcuts that are kind of parallel because the scaling breaks down. And that's actually the answer to one of the first questions people often ask about Spark is, how come it doesn't include my favorite algorithm, right? And so there's a bunch of reasons why, but one of the reasons is that some of these algorithms are either very difficult to parallelize, or when they are parallelized, they don't scale as well as the rest of the system. And so the project is very hesitant to bring in something that limits the scaling. If everything else scales linearly, and then you bring in something that scales with like square root or something like that, it's going to hold back the scalability of the whole thing. So one of the reasons why some algorithms may not be present is because there isn't an implementation that scales out quite as well. So we have this data parallel processing model, and that's going to affect how we write our code because we can't assume that we have a bunch of mutable local state, because we don't. Fault tolerance. So some of these things are maybe less interesting from the data science point of view, but important from an engineering point of view. So by fault tolerance here, we don't just mean that like if it breaks, it can keep going. But when you scale up a cluster to sufficient size, things break constantly, right? There's always stuff breaking. And so not only do you have to be able to recover when something breaks, but you have to recover pretty fast because there's going to be another failure, right? So it's not like, well, if it breaks, we can recover from that. It's like we have to consistently recover fast enough that when the next failure happens, we don't fall behind. Otherwise, you don't make any forward progress. Like you may always be able to recover, but you never finish. So fault tolerance is is an important goal and pretty interesting. Scalability we talked about. Data locality aware scheduling. So that's the idea that if we have a large amount of data, one of the most expensive things to do with it is just move it around. So what we'd like to do is ship the code to where the data is rather than the other way around. So Spark has a scheduling heuristic we probably won't talk about today, but it balances both where there's compute resources. So like if everybody in this room were a core in some cluster, it could be that everybody on that side is idle and has no work, but all the data's over here. And so Spark has to figure out, well, do I schedule things now where I have a ton of idle resources, or do I wait and schedule it where the data is? And there's some tools in there where you can tune that. But Spark is aware of that trade-off. And if possible, it will try to take advantage of that. So if you're running Spark in a Hadoop cluster with HDFS, you'll get the benefit of that. Or if you're reading data from, say, the DataStax Cassandra implementation, they co-locate Spark with Cassandra so that Spark can take advantage of having the Cassandra data locally. If you're reading data over the network, like from S3, like we are here today, at least the initial read, there's no way to get locality because we don't know where the stuff is in Amazon. It's kind of opaque to us by design, so everything looks like a network read at least the first time. Once we've brought data into the cluster and maybe cached it or made a local copy, then we can start doing smarter things about data locality. And then the last piece, load balancing. In the context of these kind of systems, what we mean by load balancing is that we try to keep all of the cores in the cluster as busy as we can all the time. So the idea is you're paying for a bunch of compute resources. You want your utilization to be as close to 100% as possible all the time. You don't want to have a situation where you've got everything busy for 50% of the job, then 50% of the core is busy for some more of the job, and then a couple stragglers that take like an hour, and everything else is just idle. So the way Spark handles this, again, we're not going to get too much into the details, but if we break up our data into enough pieces and they're of the right size, then Spark will automatically be able to schedule them and keep everything busy. So that's what we mean by load balancing. It's basically getting being able to spread the computation over our compute resources as evenly as possible so we keep everything busy and get finished hopefully as quickly as we can. So Spark is, wow, I can't believe it's almost like 8 years old now, something like that. So it was originally created by Matej Zaharia, who I think is giving a keynote here tomorrow or Friday maybe. I think he's actually here. So he originally created this when he was a grad student at Berkeley, and the goal was to leverage changes in the hardware environment, right? So people have been doing cluster computing as long as they've been doing computing, right? So the idea of scaling stuff out in a cluster is decades old, and so one might ask, if you're a PhD student, like, how do I convince my advisor to let me write another clustering system? And the basic idea is that every so many years the hardware environment changes, and sometimes these changes are sufficient that they motivate a different model for the software end of things. So in this case, RAM was a lot cheaper in the late 2000s than the early 2000s when Hadoop first started showing up in the Google papers. And networking had become a lot better, right? So in the 10 gigabits was really hard to get and required special hardware in the early 2000s. By late 2000s, 10 gigabit LAN was just commodity stuff. So the idea was let's use those things. Let's move data around the cluster because 10 gigabits is quite fast. Let's store it in RAM if we can, because we can now have these gigantic instances, 256 gig servers or even terabyte RAM servers that would have been impossible before. And let's do less with spinning disks, and maybe even not so much with solid state disks, because it's faster to get stuff in memory and move it around the network. So that was the motivation for the architecture. It's open source under Apache. The latest release is actually 2.1.1 now because it came out this morning. It will soon be 2.2.0 sometime in the next few weeks. There are some big changes in 2.2.0. Maybe at the end of the day, if you're interested, we can talk about those. And then one of the most exciting things about Spark is that it has been repeatedly re-architected for major performance gains. So if you look at what's happened over the past 5-6 years, it's not, well, they've added more APIs, or from a machine learning point of view, they've implemented some new algorithm. The entire guts of Spark have been rewritten several times. The networking layer, the processing model, how data is stored, to get gains of 10 or 100x each time. And it's pretty gutsy and it's pretty exciting. So Spark today is almost a totally different system from the way it was 2 years ago. This is kind of a blessing and a curse. It's great because it's really fast and easier to use. It's a curse because there's so much material on the internet from the old days of Spark that if you Google for something, your odds are that you're still going to find something from 2014 that's just wrong now. It may run, but it's going to be either suboptimal or may not get where you want. So it gives us something fun to work on, so to learn new stuff on Spark. So getting into the machine learning and data science piece. They didn't tell me what the schedule was for breaks. Usually for these things, well, there's two things. One is you can't sit here for 4 straight hours and stare at a screen. Even when there's stuff to do on the keyboard, it's your brain will fry. So we need breaks. But they usually schedule some specific thing with coffee and stuff, and they usually tell us when it is so that we can all coordinate that. I have no idea where that is. They didn't tell me. So we'll definitely take a break this morning, and I'll try and figure out where that is, or if someone would like to message one of the organizers or email them and let me know, we can coordinate that so you can get coffee and snacks at the right time. So sorry about that. Yeah, that's weird. So Spark for machine learning. So the first thing is, Spark is not, in its current incarnation, Spark is not meant to be the final tool to replace everything for machine learning. It's just not. What Spark is designed for, and where you want to use it, is if and only if you need to do things you cannot do in a single machine. So if you can run your stuff in R, if you're an R fan, you can run your stuff in R on a giant server instance running R, do it. You'll win. That's a great way to do it. If you can do it using Python on some giant server or whatever, and you can process your data set, do it. That is great, and it will actually beat Spark, because again, since Spark is designed for scale out, there's inherent cost to that abstraction of distributed scheduling. And so your local version of Python may beat Spark, or depending if it's designed right, it will beat Spark. So where Spark comes in is where you either need to train or you need to predict on data sets that are just way too large for a single machine. And we'll look at kind of both sides of that. So the main focus is on model building. So you've got some huge data set, and you need to build a model using distributed training to build a single model. That's kind of the core use case for model building on Spark. Once we've got a model, we also may want to use Spark for bulk prediction. So you have a model you've either built on Spark, or maybe you built somewhere else and you've brought it into Spark, And the business requirement is to do prediction on huge amounts of records pretty fast. So maybe every 15 minutes you're getting batches of like billions of records, and so you need to predict on all of those things in batches using a big cluster. So like I mentioned earlier, Spark has a fairly narrow set of algorithms and models compared to say R, but it is extensible. There's also third-party libraries and stuff available. So if you want to do a particular thing with Spark and you don't see it in the APIs, you shouldn't necessarily assume that it's either impossible or doesn't exist or that you've got to write it yourself. There are third-party packages for Spark that include quite good code. They just haven't necessarily been incorporated into the main body of Spark, a lot of times just because of, from the Apache project point of view, wanting to maintain that code properly into the future. The team wants to be a little conservative about bringing stuff in, because once they've brought it into the core distro, they're committing to making sure everything's compatible, and so on. So it doesn't mean, the fact that something is external or in some package doesn't mean that it's no good. It just may not be in the core distribution. So there's a couple of APIs that exist in Spark, and we're going to focus on, there's sort of an old one and a new one. I'm just going to call them old and new. The original one, which was, and now the project has confused things a little by using the same name for both. That makes it extra fun, right? The original one was called Spark MLlib. It was based on an earlier model of distributed data called resilient distributed data sets. Spark still uses those resilient distributed data sets, or RDDs, but nowadays they're kind of buried a little bit further down under the hood. They're almost like the assembly language of Spark. So nowadays, 95% of the stuff you're going to do with Spark, you're not going to do with RDDs. RDDs, like if you try to use them directly, they will actually perform worse. So it's one of those things where getting closer to the metal actually gives you worse performance. So that's not how we do most things, although you may need to do it if you're implementing a new algorithm. The newer API, which first came out about 2 years ago and is now pretty much replacing the old one, is called Spark ML. Or the ML Pipelines API. So this newer API is based on data sets or data frames, which are kind of abstractions of queries. It's kind of an abstract version of a view or a table. Much easier to use, and we're going to focus mostly on that. As soon as the new API reaches feature parity with the old one, it's about 98% of the way there. 2.2 should get it like to 99%. Sometime around the 2.2, 2.3 timeline, the old API will be deprecated and then will be eventually removed. So the older API is going away. And we'll kind of talk about where we still might end up using that and where we wouldn't. So the purposes of switching to this data frame-based API. So first thing, because some people here, a lot of people are new to Spark, what the heck is a data frame? The data frame system in Spark was designed to unify a few different things. So if you're coming from something like pandas, you may have a feeling for what a data frame is. And one of the goals in Spark was to make it somewhat friendly to people coming from pandas, but it's not actually the same thing. Right? Like if you have a pandas data frame, you can go around and poke at different elements in that table or that structure however you want. That's very different from Spark, where the data frame is more of an abstract thing. It's kind of like a view in a relational database. So it's a description of a query. And a data frame, you might build up a data frame by composing other data frames, the same way you might make a view in a SQL database by defining a new view over other views. So the advantages of this more abstract approach are that we can do optimization and lazy execution, but it takes a little bit to get your head around because you can't just go like row by row changing things or whatever the way you might if this thing were local. So that's sort of a similarity and a difference to something like pandas data frames. The data frame system in Spark was also designed to kind of unify an internal implementation of SQL. So prior to this, there had been some other, the history isn't important, but there have been some other attempts to get SQL to work on Spark. The official data frame stuff said, okay, well, we're going to have a data frame API that looks a little bit like pandas and a little bit like R, and we're also going to have SQL support, and the SQL support is going to map directly to data frames. So Spark has its own SQL parser. When you punch SQL code into Spark, it basically gets processed directly into data frame operations. So these things are unified. And it provides a way to do query optimization. So in the bad old days of Spark, your brain was the optimizer. If you wrote the wrong code, your stuff would blow up. If you wrote bad code, your stuff would run slow. What you wrote is what Spark ran. So you had to be pretty clever to get your stuff to run well. The idea with the data frame API was, let's try and be more like a database in the sense that you should have more flexibility in how you write queries and code, and Spark should be able to do the obvious things in terms of optimization. So the data frame API creates this kind of abstraction layer that allows Spark to do it. So when you come in and you say, I want to take this data frame and I want to filter on some column, in the old days you were punching in code, Python code, Scala code, something like that, and Spark was scheduling your exact code. Nowadays, if we take a data frame and we say filter, or you do a SQL statement, you say select from where, Spark treats those as purely logical things. It says, okay, I get it. I get the idea you want to do some filtering. Let me handle how to do that. And so it has actually, as of 2.2, like 2 different optimizers, one that has a bunch of rules for fixing queries, improving them, and another one which is brand new, which is a cost-based optimizer, where it can actually use statistics about the data the way an analytical database would to do, say, filters in the correct order, things like that. So these are kind of the user-facing advantages, and then under the hood, they've also spent a ton of time over the last 2 years building improvements in terms of how the data is represented. So again, in the old days of Spark, you were processing, if you were writing code in, say, Scala or Java, you were dealing with Scala or Java objects, like a java.lang.string. Or if you wrote your code in Python, you were dealing with a Python string or a Python dict or something like that. Nowadays, you may be talking in Python or Scala, but the data itself is represented in a native language neutral format. So the strings are UTF bytes in memory. And they're not even in the JVM's managed heap of memory. They're off heap, so they don't affect the garbage collection. They're very compact. They're very fast. The internal caching is columnar, so if you have a 1,000 column wide data set, you only need 1 column. Spark can do that really efficiently. Anyway, all of these kind of improvements are somewhat hidden from you under the hood, but that kind of motivates why we want to use data frames as much as we can, because we get all of this stuff for free. So we're going to be using it as much as we can for our machine learning APIs also. So all of the modern Spark APIs are built on data frames. So graph analytics, regular old querying, machine learning, et cetera. And I'll show you the kind of the APIs and how that works. This class is mostly in Scala, but if you're new to Scala, don't worry about it. The Scala we're doing in here is super simple. Sometimes people come across Scala and they've seen a video or gone to a meetup and they're like, oh my God, this stuff is insane. And there is really cool, insane stuff you can do in Scala, but we're not going to do any of that. And you don't actually need to know any of that to use Scala with Spark, or Spark with Scala. Even the Spark code base, which is written in Scala, is written in a very explicit, almost Java kind of style. You do not need to be a Scala guru to work with or even on Spark. So I just want to kind of make people feel better about that. Why would I do stuff in Scala here and not Python? Obviously, Python's a much more popular language for data science, because if you're extending Spark, you kind of need to do stuff in Scala, since Spark is written in Scala. So if we add an algorithm to Spark, we're going to add it in Scala first, and then if you want your colleagues to program it in Python, you just put a Python wrapper on it. There's a pattern for that. And the truth is, the code isn't all that much different. The biggest difference is that, like with Scala, you can leave parentheses off a lot of method calls. So if I switch to Python, I'll forget those, and I'll get a nice little message from Python saying, hey, you've got to call this thing. But the APIs are pretty similar. In terms of docs, so just, most of these you could probably find, but these are some places that you want to go. So under spark.apache.org, you can go under docs and latest version. And there's an entire little mini site, I'll click on this, we'll go through and take a look, which is just devoted to machine learning. So you can look at the API docs. The API docs are not very communicative about machine learning stuff. Like, they'll list the names of the classes and the names of the parameters, but they don't tell you the meaning. This is the site you want to go to when you're trying to figure out how to actually use this stuff. And we'll look at some of these things today. So for example, if you wanted to say, well, I need to do a particular processing on my features, how can I see what the options are? You could click here under extracting, transforming, and selecting features. And you can come down here and look and say, oh, cool, polynomial expansion. That's what I need to do. Click through to here, and then there's nice examples in different languages. So here's an example in Scala. Here's an example in Python. So definitely want to be familiar with this site in terms of the docs. It's much more useful than just the APIs. There are API docs. There's also this site from Databricks down here. Interesting. Let's see if let me try that one more time, see if I can get to there. I'll just punch it in directly. So there is a site called docs.databricks.com. Here we go. And the reason I mention this is because even if you never use Databricks, about 80% of the content in here applies to open source Spark. So even though it's called docs.databricks.com, and there is some Databricks-specific tool information here, like how to use notebooks, if you go into here on the left, there are a lot of examples that are just pure open source Spark. So like if you click binary classification example, this is applicable no matter what flavor of Spark you're using. So there's lots of great examples on how to do stuff in here. Let's do something with some actual code, because it's almost 10 o'clock, and the longer we go without actually having code, the worse I feel, or maybe the worse everybody else feels too. So let's come in here and let's see where we want to start. Okay, there's a Scala cheat sheet notebook. I'm not going to go through that here for time purposes, just because it might be useful, but we just don't have the time for that. I will do this data frame cheat sheet. Because so many people here are totally new to Spark, and everything we're doing here is with data frames. So I want to remove a little bit of the mystery about how data frames, how to use them. We're not going to talk about how they work today. We just don't have time for that, but we can at least try them. So what I did to get here is I went under Workspace to my folder for the session today. I went 01 data frame cheat sheet. And then the next thing I have to do is up here it says detached, which means the notebook is not talking to any Spark cluster. So I'm going to pick my cluster here and go attach to. So now I'm attached to my demo cluster, and now I can hopefully run some code. So the first thing I'm going to do is, this is maybe the easiest way to just look into a file and start querying it. So there's other ways to do it, but we can go like this. %SQL is a magic tag, kind of like in Jupyter. And what this is a shortcut for doing spark.sql and then passing a string. And then it gives a nice pretty display. So that's what the %SQL is. And then I'm telling Spark that I want to read everything from this particular data set. So this is a file path in DBFS. So this data is technically out in S3, but it's mapped under this path. It's an Amazon data set. And this parquet.backtick thing is a way of giving Spark a hint about the format of the data. So what I'm saying is this is stored in a Parquet format. I mean, we might talk about Parquet later. But this Parquet is a columnar. It's a columnar compressed data format. It's a static format. But it has a lot of really nice properties. It's based on Google's Dremel paper, and it's the best performing static format for Spark. It's not part of Spark, it's just open source, but it happens to work really well. And so I can just run that and get data back. So this is kind of literally the easiest way. It's like I haven't done any work to set anything else up. You can see there's no magic here. I just basically told Spark, hey, there is Parquet data, here's where it is, run SQL over it, and it works. And so I can do that. So now we can run some query here. We may play with this a little bit later. Now, SQL is great if you're doing just interactive exploration, but if you're writing some kind of a program, you probably want to manipulate your data programmatically and not have a bunch of SQL strings. So there is a kind of domain-specific language or an API for talking about data frames and queries that parallels the SQL world. So we're compatible with SQL 2003 and also HiveQL, but we can also go and create objects that represent these things, and it would look something like this. If we wanted to do this query using code, we would say Spark. So what Spark is an instance of a class called Spark Session. It's kind of the entry point for messing around with Spark 2.x. Where did it come from? in interactive environments like this notebook, oh, and by the way, I always want to mention an open source, if you want a notebook experience and stay in the open source world, Zeppelin is, you guys know about Zeppelin probably. The Zeppelin Spark support is really nice right now. A year ago, things were a little sketchier with Zeppelin. It was great, had a lot of potential, but there were a lot of issues. Lately, Zeppelin is really kind of hitting its stride. It works beautifully with Spark. You can just download that. It comes with Spark embedded. You don't have to do any other work. Turn it on, and you get something very much like this, totally open source and free. So in an environment like Zeppelin or here or the Spark shell, you just have this object called Spark. It's injected for you. If you're writing your own program or script, you would instantiate a thing called Spark session, and that would give you this guy. And then we're going to say .read, which gets us a helper for reading stuff. And then we're going to use a shortcut. We're going to use a shortcut that says just read me some Parquet data. So .parquet is short for format Parquet and then load. And we're going to point it at this file. And when I run this, so while this is spinning, over here on the left, this val, by the way, that's the only weird thing you'll have to learn today about Scala, you'll have to get used to, is you have to declare your variables in Scala, unlike Python, and you typically use immutable handles in Scala. So we mark those as val, which is like a constant. If you want something as mutable, you put var. That's probably the only weird thing we'll see. So now what I have is a thing called, I have an object called myDataFrame. And you can see I get this nice little feedback here that says that's org Apache Spark SQL data frame. And it looks like this. Rating, which is a column of doubles, and review, which is a column of strings. And what Spark did is it just went out to that file, read the metadata. So one of the nice things about Parquet is it's self-describing. So Parquet files include their own column names and types and structure. So Spark just takes a little peek and says, OK, great. I know a lot about this table. It looks like this. If I want to look at it, so how do I actually see what's in there? So to get the pretty view in the notebook, I would say display my data frame, and that will give me something that looks exactly like what I saw above. So a nice HTML table. If I'm working in more of a text world with just raw Spark, I could say myDataFrame.show, and I'll get this kind of ASCII art version of the table. Right, so this is how I can go ahead and create a data frame or a query. And I can modify this query by adding operators onto it. So let's say I just want the review column. I can say select review. And again, this is really what I'm doing here is composing queries. So this doesn't do any computation. What this is doing is just saying I had a query for my data frame. Now I would like to treat that almost as a subselect and make another query that selects just review. Every time I modify or touch or alter this data frame, I get a new one. The data frame itself is immutable. If you're worried that that's expensive because, hey, I'm making 1 million data frames and the data is really big, these are just symbolic. We're not actually moving the data through these things. Processing is lazy, and before Spark actually evaluates the data, it's going to optimize the query. So if I have some ugly composition of 100 subqueries that are filters, they'll all get collapsed into a single filter before it runs. So don't worry about that. Let's see, we already did this, so we already did a display. You can try that if you want. We already did a show, so I've kind of demoed those. Here's an example of doing a filter in the DSL or in the data frame language. You can say .filter, and you can provide a little SQL snippet like this. So here I'm saying filter where the star rating is greater than 4 on these Amazon reviews, and then count them. There are other ways to specify filters that are more object-like even inside there and less string-like, but I'm not going to talk about those unless you have questions. If I want to do some aggregations, like I might want to say, well, how do these things distribute over rating? So let's group by rating and count. So this gives me back a data frame. If I want to see what's in there, I can do a show on there. And now I can see how many reviews we've got with different star ratings. Here's an example that's not too exciting, but it shows order by, right? So now I've done a group by and an order by to see, where the, which ratings have the most reviews. If I have some data frame like this and I want to talk to it in SQL, I can say create or replace temp view. So here I'm saying I want to take this data frame, I want to find the records where the rating is 5, and then I want to give this thing a temporary view name called Amazon 5 star, and now I can query that using SQL. So why would I want to mix these up? Well, either because sometimes there's some complicated windowed aggregation that's just easier to write in SQL than try and figure out how to write in the code API. Or maybe I'm working on a team and some people are using tools so Spark can actually speak JDBC over a port. So somebody's using like Tableau or some other visualization tool, they can actually connect. I can come in here and be writing some queries and defining some views, and they can actually come in through the JDBC port and query those same things if I do this. So it all kind of connects together. This is what it looks like to run SQL without the magic tag, just so you can see what that looks like. This is pure. In the pure code, it would look the same in Python, except in Python I have to put the parens there. Once I've got one of these things, let's say I've done some cleaning, like I've got a bunch of really ugly data, I do some transformation or cleansing on it, and I want to write this out to a data set for somebody else to work on. I can take a data frame and I can call .write on it, and that gets me a helper for writing. And then I could do things like say I'd like a header row and I'd like to write it out as CSV, and I can go like this. Right? So I started with Parquet. I've now found the 1-star product reviews, and now I want to write these things out as a CSV table for other people to look at. And now we can look in there and see what that looks like. Now that looks a little bit weird, right? So I wrote this out as a CSV file, but when I list, it looks like this. What's that all about? So because Spark is designed to do stuff in parallel, we don't want to bottleneck by taking some enormous data set and then how do we get it into one file? We've got to run it through one place. Don't do that. Spark won't do it. People often feel uncomfortable with having their data in lots of pieces, and so they want to put it into one file. If you look on Stack Overflow, there's a zillion people saying, how do I have all these partition pieces, how do I get them all into one file? One of the standard answers, which you also do not want to do, is use a call called coalesce, which forces Spark to merge those partitions into a single giant partition. That's bad for more reasons than I even have time to talk about today. Unless the data is tiny, in which case you don't need to be using Spark. But if you really have data at scale and you try to coalesce it into a single partition to make the file look pretty, it's just not going to play right. So what you can do is write it out as a bunch of pieces. If you really need to merge those, use some other tool to just merge the actual files. But in general, it's probably better just to leave them in pieces. Spark doesn't care when you point it at a folder or a file. If it's a folder with 100 pieces under it, Spark will just process them all. So you don't have to do any special work to iterate through pieces or anything like that. Everything is designed to work in bulk. So my CSV file actually ends up in these different pieces here. How many are there? It looks like there are 8 different pieces because I had 8 partitions in my data set here. If I want to read those back in, I don't have to care about any of that. Notice when I read, I just point at that same folder, and Spark knows what I mean. It means process everything in there as part of a single data set. So it comes back in just fine. So that's all I was going to show here. This is kind of like the 3-minute introduction to data frames. And what I wanted to do was give you just enough sort of code you can copy, paste, or play with that you don't feel like totally behind when we start using data frames for other stuff. And now we can move on to some more machine learning kind of things. So since I'm going to start with, and again, I apologize to a couple of people here that are maybe have been doing this stuff for a while, but because so many people here are pretty new to Spark, I'm going to start with a couple of notebooks that demonstrate just doing some basic stuff so we can talk about how to do this kind of the Spark way. So the very first thing we're going to do, this is the world's least exciting data science project here, because first we're using the Diamonds data set, which, raise your hand if you've seen this before. Probably everybody has seen Diamonds before because it's part of R. So that's not exciting. And we're doing a 1-variable linear regression, which you might have done in high school using a pencil and paper. So, but the reason for that is that I want to focus on how to do this stuff with Spark. I don't want to do anything with complicated or tricky math or data because that's a distraction here. What I want to do is do something simple and talk about how we would solve this with Spark. And then we'll look at more complicated things. So the data itself is already here. I tried to run this cell and I got this nice friendly error message. Hey, this notebook is not attached to a cluster. So I can click attach and run, and Databricks will attach this. So the %fs ls is one of these magic tags for doing a file system listing. This is the data over here in DBFS, the CSV file, if I want to look at it, how would I do that, right? And this is a common thing. If you're new to Spark, you go, well, how do I look at a file if I can't just type head on it, right? Or like, you know, how do I see this thing? It's distributed out somewhere else. So if you have no idea what's in a file, we can do this even simpler. If you have no idea what's in a file, this is what you want to do. Spark.read.text, right? Now this won't try to interpret the data. It'll just assume that it's some kind of text, and you can take a look at what's in there. When you do a .show, Spark automatically adds a limit operator. So you don't have to worry that there's a trillion records, you're going to pull them all back into your browser or something. It'll automatically limit this, and you can see what's going on. So this is, if I had no idea what was in here, I would do something like that and say, okay, interesting. So it looks like I've got, you know, a header row, and I've got some, I've got row numbers, and I've got something going on here. If you pass false here, then Spark won't truncate the rows, so you can see a little more of what's going on. So if you have no idea what's in a file, you just want to see what the heck is in there in terms of some text, spark.read.text. Now once I'm convinced that it's CSV, well, I'd like to be able to parse that. So I'm going to go, let's do a spark.read.csv. So this is kind of parallel to what we did with the Parquet example, except I'm telling Spark that it's CSV, and I'd like it to try and parse that. So if I do that, I get back a data frame here, and if I do .show, let's see what that looks like. So I'm making some progress, right? So Spark found the delimiters at least. It hasn't figured out the header row piece, so I've got these bogus column names. And we'll see that there's also maybe some type problems on these, so we'll figure out how to fix those next. If I want to read a header row, I can do this, option header true. It's exactly what it sounds like. It just treats the first row as a header and uses those as the column names. So that gets me something that looks a little bit nicer, right? So now this starts looking more like a real table. Now I know if you're coming from like R, people are like, oh my God, I can't believe we're doing all this, we haven't gotten anywhere. Because in R, it's like you solve the whole problem with one line of code in like half the time with R. But hopefully by the end of today, you'll feel like in Spark, it's not that many more lines of code to do this stuff. Okay, so the next thing I want to do here is see if I can fix up the data types. If I don't tell Spark anything about data types, what it's going to do is treat everything as a string. And that's for performance reasons. So Spark can try and figure out the types, but in order to do that, it has to look at all the data. And so again, Spark is designed to work well when you have huge amounts of data, and they may be different every single time. So you may not want to invest the time to do a lot of reading here just to get the data types. We'll look at some other ways later of dealing with that. But what I'm going to do here is go infer schema true. So this is mildly expensive, but what it'll do is it'll take pretty good guesses at the data types. Like if they're all numbers with no decimal points, they'll show up as some kind of integer. If they have decimal points, they'll show up as some kind of float or double. Otherwise, some kind of a string. I'm also going to select out just the caret and price columns, because here we're just doing one variable, so we can pull out just those columns. This thing here with the apostrophe, so I could have done these with strings, with quotes. The apostrophe is a Scala symbol. It's kind of like the colon syntax in Ruby. And Spark has a helper that converts symbols to columns with the same name. So if you want a column object in Spark, the easiest way in terms of literally using your fingers is to put apostrophe and the column name. There are other ways to do it that all involve more keystrokes. So the lazier you are, the more likely you are to want to do something like that. So now what I have here is a data frame with just these two columns, caret, which is a double, and price, which is showing up as an int here. So maybe I want to sample this and take a look at a scatter plot, right? So that might be something if I want to see if there's any hope for a linear regression. So what I'm going to do here is sample this. I'm going to do that for two reasons. One is, well, this diamonds data set's not that big, but in real life, if you're using Spark, you probably have a very big data set. So you want to downsample it. The other thing is, when Spark, although usually when we're processing data in Spark, we don't think about it as being ordered unless we've put an ordering operation on there. Spark does not shuffle or reorder the data just because it feels like, because that's expensive. So what's going to happen if I don't sample this is I'm going to see the first set of records, which in this case are not at all representative of the overall diamonds data set because the data is kind of ordered, right? So we need to downsample for size and also to make sure that we see from stuff throughout the data set. False means sampling without replacement, and 0.01 is the probability of including each record. So it's approximately 1%. And I've pre-configured this notebook to do a scatter plot, and we get this nice picture. It looks like this. So we can kind of see, yeah, for the cheap diamonds, the linear regression looks like it might work. For the more expensive ones, it's probably not, but we'll see how it goes. And there's some little widgets down here you can use to configure your plotting. So you can generate visualizations in the notebook and customize those using a little GUI. If you like this, but again, you can't use Databricks or don't want to, Zeppelin has a very similar widget for doing this stuff. Maybe we want to calculate Pearson correlation on these columns just to also get some high-level idea of what might be there. We could do something like that. If you call .stat on a data frame, you get access to some statistical helpers. And then I can call .core and pass column names and get a correlation here. So, okay, so how would I actually build a model with this? So all of the algorithms in Spark, so the beautiful thing about Spark ML is even if you've never used it before, is there's not too much to learn because everything in Spark follows a very strict pattern. So every single algorithm we ever process is going to take vectors of doubles as its features, like no matter what. So we have to get everything into a vector of doubles. Some tools, again, you may be used to that will do this automatically for you, and Spark does have some helpers that can help, but we do need to think about it a little bit. We're going to use a helper here called a vector assembler. So vector assembler is in that doc site, and it's a subclass of a thing called a transformer. So a transformer is the first kind of key piece of the Spark ML API that we want to talk about. Transformers are the simplest things that we're going to come across. They're really common for doing feature processing like this. And the key piece, we're going to write our own transformer by the end of the day. And the key piece about a transformer is that it encapsulates all of the logic that we need to operate on these rows. Typically, it does per row operation, so it's very easy to parallelize. That's not 100% true, but 98% of the time, the stuff we're doing in a transformer is operating on each individual row by itself. Like in this case, we're making a vector from data in one row and separately making another vector from data in another row, and so that can be parallelized for us really nicely. And feature transformers don't produce any interesting internal state. They just do something and you get output. The output is going to go into a new column in the data frame. So to operate one of these things, we just have to instantiate it, tell it what the input columns are and where it should put its output, and then we can go ahead and run it. So we're going to go set input calls, and since we're in Scala here, we'll pass an array. If we were in Python, we could just put a list, like a Python inline list of the caret column. The output will write into a column called features. And that will give us this vector assembler object. So to use any transformer, we're always going to do the same thing, which is we're going to call the transform method. So that is the way you run transformer no matter what it is. So we can say assembler.transform and then apply that to our data frame, and I'll show you what that looks like. So it comes up looking like this. We've got, here's the original caret and price, and now we've got another column added to the data frame. So in this model, we just keep kind of modifying these data frames and adding new things on, and we can talk about where data is just based on its column name. So the next thing we can do here is, we don't have to do much other prep here. Let's just add a linear regression algorithm. And so I'm going to import the relevant class, and then what I'm going to do is instantiate this thing, so new linear regression. And I'm going to tell it where the label or response variable lives. So I can skip some of these because there are intelligent defaults. The default for the features is called features, and the default for the label is called label. So if those names line up, I don't have to put this there. In my case, because the label or response is actually in a column called price, I have to go and put that here and say set label col price. So here's my linear regression algorithm. And then we can go and build a model. So what I'm going to do first is do a training and test split here. And I'm going to do that using this helper called random split. So I'm going to create a split of 75% and 25%. This number here on the right is just a seed, so we all get the same results. And that's going to give me arrays training and test, or sorry, data frames training and test, which I'm going to destructure and assign into an array here. And then what I'm going to do is I'm going to apply the linear regression to the adjusted data. And so the way this is going to work is linear regression, and every algorithm in Spark is a subclass of a thing called estimator. And I'll review these APIs in the slide deck in a minute. But we have these transformers, which go usually row by row and don't build any interesting state. Then we've got these estimators. And so some of these patterns are kind of inspired by scikit-learn. So they're designed to kind of play well with your intuition there, maybe a little bit, but they don't work exactly the same way. And the estimator's job is to look at a bunch of data and calculate some valuable state. So we could be using an estimator to do feature transformation, where the valuable state is maybe a lookup table for different values in a column. In this case, the estimator is a ML algorithm, and the valuable state it produces are the coefficients in the model, the weights. So we say .fit to actually calculate that state, and that's going to do all of the work. And what it's going to do is it's going to spit out a model. So a model is a subclass of transformer. And estimators and models always go in pairs in Spark with a strict naming convention. So if the algorithm is called X, is just called X, when we call fit on it, we're going to get an X model. So if this is called linear regression, we're going to get out a linear regression model. So we've got this naming convention for this. And we're always going to call the same methods on there. So we're going to call fit. And what we're going to call fit on is the result of doing the vectorization on the training set. So we go assembler.transform on the training set, and then linear regression.fit on the result of that. And that gives us our linear regression model here. And then to apply that model and make predictions, we're going to go lrmodel.transform, because again, models are transformers, so you use them by calling transform. When you run them, they produce predictions. Where do the predictions end up? Well, there's a default column name for that. So if I wanted to change the output, I could do that, but here we're going to go with the default. And I'm going to pass the adjusted version of the test set, and I'll show you what that looks like. So it has a .show on there. So we get a prediction column over here, and we get some prediction values. So if you look at the way we did the code here, I broke this up into really small steps and made it really explicit, because I wanted to kind of take the mystery out of what each piece is doing, right? We've got the assembler, and we do transform, and then that gets fed over to here, and then we use the same set of steps on the test data and feed that to this. And hopefully, does that more or less make sense? So hopefully that's really clear. But you won't see examples like this online, and you won't write examples like this yourself, because it's too tedious. Like, once you've got lots of processing to do and lots of steps, all this composition of functions gets really crazy, and it's just a big mess of code. So what you want is a nice way to simplify the steps and have Spark do the work. So that's what we want to look at next here. And the tool for that in Spark ML is called a pipeline. So the idea is that a pipeline is a wrapper for a set of data processing stages. And so if I want to represent this pipeline, I would say new pipeline, and then set stages, and then pass the assembler and the linear regression algorithm. And this pipeline is itself an estimator, so I can use this to fit data. And how does Spark know how to use the pipeline? Well, that's where this sort of Lego brick, snap together, very standard API fits in. Spark is just going to walk through the pipeline, and if it sees a transformer, it's going to say, okay, great, let's call transform on the current state of the data. If it sees an estimator, it's going to say, great, let's call fit against the data and then transform using the resulting model. So because that pattern is so rigid, Spark can just automate that. So Here, you may not feel like it's buying you that much, but if you have a complicated pipeline with 10 or 20 steps in here, this is going to be really handy, right? And plus, we can describe this without regard to the actual data. So notice the data frame itself doesn't show up in here anywhere, right? So I can write a pipeline that describes what I'm doing, and I can even compose pipelines, and then later I can apply them to data separately. So to actually go ahead and do that, I can just go pipeline.fit, and that's going to get me a pipeline model, because remember the rule is always estimator and then model. So if we have a pipeline, then it's going to produce a pipeline model. And that's this guy here. And then if I want to make predictions, I can go model.transform, and I'll get predictions. And Spark will take care of applying the same data transformations to my test data that it did for the training data. So all that stuff just lines up, and I don't have to worry about it. So it's the same thing I did manually, but this just saves me having to code that. If I want to take a look at these, I could maybe do some kind of a plot here. So let's see, here we have a row format. Let's see, we can do maybe a scatter plot. So here's a scatter plot. So we can look at like prediction versus price. That's pretty much what we expected, right? It looks pretty good down here and comes apart up there. So we can extract training and test information from this. So first, let's look at training information. So this is a little kind of a little contortion I have to do because Scala is very particular about strong typing. So you wouldn't have to do quite this much stretching in Python. And that what I'm doing here is saying I want the last stage of the pipeline model. And what I want to do is downcast it to linear regression model. So this is where Python sort of looser typing would help me out. I might not need to do that. I'm going to call has summary, and this tells me, yes, I've got a training summary. Training summary are statistics about how well we were able to fit the training data. So let's extract that summary and see how we did on the training end. So if I call .summary on that model, I get a training summary, and from the training summary I can find out things like the apparent error or how well we fit on the training data. So I could say what was like the R squared or what was the RMSE on the training side. And so it looks like this. I can also pull out the training residuals. Maybe I want to do a plot of those. So I could look at this and say, oh, okay, well this is useful. So it's this isn't too crazy. It tells me that the algorithm was able to more or less fit the training data in a sensible way. So this gives me some hope that this might work. And if I want to figure out how we did on test data, we're going to use something called an evaluator. So I will review these classes, but the key pieces we've seen so far are transformer, estimator, and now we're looking at evaluator. So we're halfway there. There's only 6 of these in the entire API. There's really only 6 classes you ever need to work with to solve pretty much everything you want. So we've covered about half of them. So evaluator is the thing that knows how to calculate specific statistics for the kind of problem we're doing. So there's regression evaluator. Later we'll see things like multi-class classification evaluator that knows how to do other statistics, etc. So here we'll do a regression evaluator, and we're going to tell it where does the price live and where does the where does the label live and where does the prediction live. And that will give us an object like this, and then we can say evaluate on that data set, and we get back some number like 1541, and we might say, well, wait, what the heck is that? If you call getMetricName, you can see that is RMSE. That's the default. A lot of these objects, by the way, have some neat help. Like if you don't want to look in the docs and you're not sure what's going on, you can go explain params. So this is almost all of the API objects in the Spark machine learning library have this explain param. So you do this and they will tell you what parameters they support, what the valid options are, what the defaults are. So we can see if we wanted to switch to some other kind of metric here. So how is the 1541? If we call .describe on a data frame, we get summary statistics for the columns. So if I do a .describe on the test data, we can see the price, the standard deviation on price was 39.61. Our RMSE is 1541, so we've learned something. It was not a great solution to the problem, but we've extracted some information from the data. If we want to get other statistics, we can switch the evaluator into a different mode. So we can say I want R squared here by doing a set metric name, and then do an evaluate there. So one of the questions people always have at this point is, why the heck do I need to do this, right? Like in R, again, like you run something, you get a nice report. You get a report with all the statistics right there. Why do I have to do this modeful switching thing and run separate jobs to calculate these statistics? So there's a couple reasons. One is we don't necessarily want to calculate a bunch of statistics we don't need to if we're running it over large data sets. But the specific reason for the structure is that these evaluators are not just for us as humans. Spark is going to use these evaluators when we want to make Spark tune the model. When we talk in the next lab about doing hyperparameter tuning, we need to tell Spark how to know whether one model is better than another. And so Spark is going to do this by kind of wiring all these pieces together itself. And we're going to give it an evaluator, and it's going to use that evaluator to determine how well the models score. So that's why these things are kind of structured in this very explicit way. It's not just for us, it's that they're being automated by Spark as well. So, okay, so we did about as well on the test data as on the training data, which is reasonable for what we're doing here. The last things I'm going to do in this kind of first lab piece is show you how we can extract data from the model. So most of these models we can crack open and get the information out. If we call like .intercept and .coefficients here, we can get the intercept and the weights for the variables here. So why would I want to do that? Well, if I had standardized my data ahead of time, then this would tell me things like the significance of the different parameters. It's also useful going back to that question I mentioned this morning about like how do you operationalize this? So let's say you build some model over 1 billion records using something like this, but then you want to run it. Maybe you want to run it in a very low latency environment like scoring something inside of another web service where it's very fast, or you want to run it in an embedded device or something. Once we've got the weights, most of the time the inference phase is pretty fast. We could just re-implement this, or plug this into a different environment. So we can use that to do prediction. So let me take a break here for a second. I'm just curious, did anybody find out when if there's a schedule of breaks or?
Right now.
It is it? It probably, well, I mean, this would be the time, right? Because I think we're going for, is it 9 to 1, something like that is I think the session. So I honestly don't know. Maybe I'm going to, actually, here's what I'm going to do. I'm going to pause for 1 second. And I'm going to email and see if I can figure out.
For today, there's no scheduled time, but for the other days, the coffee break starts at 10:30.
Oh, okay.
Yeah, so that's not.
Oh, interesting. Okay. Well, Okay, well, let's take a quick break then. This is we'll take like a 10-minute break, just because we need to get a chance to move around at some point. And yeah, I'm sorry. I'm surprised. It's so weird that there's no like official thing. But okay, so I guess we'll come back in about.
I think they were doing coffee after 11:15. So.
Oh, there is 11:15.
This is mentioned in the line.
Oh, cool. Can I apologize. Can I take a look? They didn't send me the same material. Coffee, 11:15. Oh, okay. So there is an official break at 11:15. So I guess what we'll do is we'll conform to that then. Thank you. Cool. Okay, so let's dive in a tiny bit deeper here, and I think we'll do one more kind of intro exercise here, which also uses this diamonds data set. We'll try, but here we're going to try and hit a couple of use cases that we haven't seen yet. So we kind of cover all of the basics, and then we'll go into the more advanced stuff. In terms of the patterns, just to kind of recap what we've seen so far and then where we're going. So we said the first kind of fundamental piece is a transformer. And this is kind of the standard way we're going to do lightweight feature transformation things. So later when we want to figure out how to deskew data or impute data or something like that, we might write some raw code first to kind of experiment and get our code right. But if we want to make this usable by other people and make it work with the pipelines and support persistence to disk and everything else, we want to wrap it up so that it follows the pattern of a transformer. So this kind of summarizes the key pieces of a transformer. So we're going to be usually processing features, although technically you could do whatever you like with it. They're typically a map type operation. If you're coming from like a Hadoop, like a MapReduce kind of world or functional programming world, they're kind of like map operations. If you're coming from a database world, they're kind of like select operations. An example would be like that we'll use later is like a binarizer. So let's say we want to just take everything and threshold it, right? Below a certain number goes 0, above that goes to 1. That's something that we can do to each individual value. We don't have to care how many values there are or where they're physically located. So it's very easy to parallelize and very inexpensive. Occasionally, these things can contain a reduce operation, so something that actually has to look at aggregate data over all of the rows. This is going away. This is kind of an anti-pattern. It's kind of, I think it's going to be refactored to fix this at some point. Unfortunately, now that would make it a breaking change. So I don't know exactly when that's going to show up if it's not in 2.2. But there are a few examples, like for example, a one-hot encoder, the way it's done in Spark, is done as a transformer. Which is a little bit weird because to do the one-hot encoding, you need to know how many values, what the cardinality of the column is, which means you have to look at all the values in the column, which means you've got to aggregate. So it kind of breaks that pattern a little bit. But in the future, I think the goal is to keep this a little bit more pure, so not to have these reduce or aggregates in transformers. You always run them by calling .transform. And we're going to extend Spark later by implementing either unary transformer, which is like a simplified transformer that just has one value in and one value out, or the generic transformer trait, which is Scala for interface, that can take multiple columns in and produce one value going out. To recap the next thing that we looked at, estimators. So estimators provide more complex feature processing or building a model. An example of the feature processing would be if we want to index strings, right? We've got a bunch of strings. We want to convert those to numbers by building some kind of lookup dictionary. So there is a helper called string indexer. Because string indexer looks at all of the values and then builds this lookup dictionary, it's implemented as an estimator. So you tell the string indexer to fit your data, and it spits out a string indexer model. And the string indexer model actually does the transformation to put the numbers in the appropriate column. So typically we're going to have one or many reduce operations, not always, but usually. If we're running any algorithm, all of those Spark jobs that are kicked off to actually build the model are all part of this estimator execution here. And the estimator is going to spit out or produce a model which is an instance of transformer. And that transformer is going to encapsulate whatever valuable state the estimator came up with. So in the example we just did, the linear regression figured out useful weights. It bundles up those weights into a linear regression model and spits that out, and then we use the model. So we're going to follow that same pattern later today. If we want to implement an algorithm, we're going to build an estimator that figures out some state, and then that literally gets passed to the resulting model as a parameter to the constructor. So it's very straightforward to code that. So that's how that piece works. We talked about pipelines, right? So pipelines represent composing transform on a number of transformers and fit and then transform on estimators. If you're coming from a functional background, you might think of this as point-free style. So the point-free style is where you describe kind of composition of functions, but not the final parameters. So like if you want to do A, B, and C to something, you come up with C applied to B applied to A, and that's kind of your operator. Then later you can pass some data into it. And pipelines are estimators themselves. So they support composition with other estimators and other pipelines, so you can build complicated setups. They can be persisted to disk and recovered and everything else. This just kind of helps you visualize if you're still not totally clear on what's the point of this pipeline. If you have something relatively simple, like let's say we want to run transformer 1 and then transformer 2, Then we want to do a fit and apply with estimator 1. Maybe it's like a string indexer. And then fit estimator 2. Maybe that's a logistic regression. If we wrote this out the long way, it would look like this, right? Literally, it would be this much of a mess. We would have to use the first transformer to do the transform, then feed that to the second transformer, then feed that to fit on the first estimator, then take the result and call transform, and then feed the same stuff back into that, and then feed that into fit for the second estimator. Right? So even a very simple pipeline becomes just a crazy mess if you were to write it all out the long way. So of course you'd write a recipe to automate this, and that's what pipeline is. So in Python it looks like this: pipeline stages equals, you just list the stages and then go dot fit. So once you get used to which pieces you want to use and like what they're going to do for you, you will get pretty fast at it. So like at first, coming from R or even like scikit-learn, it may seem a little laborious, but once you get used to it, it can be quite compact. And you can write your own helpers on top of that as well. So that's the pipeline piece. So the purpose of this uniform API is to have a single, yeah?
Pipeline's case, how complex the pipeline can be. Like, the example you're giving is more of a linear steps of more fitting and estimation. How about, say, a typical pipeline can be a directed acyclic graph?
Yeah, so
How is it handled?
you can certainly reuse stages. So you can compose pipelines inside of other ones in terms of making them. So the question is like making them not just linear. So you can reuse stages. So like you could have some data and you could have a pipeline that goes this way and another pipeline that goes somewhere else, and maybe another pipeline that composes those guys. The one thing I'm not so sure about is merging those things back together. Whether that's, honestly, I should look that up. I haven't seen a lot of examples of that. It might be possible. I mean, you certainly can do joins and stuff like that. Like in the data frame API, you can do joins and unions. In terms of the pipeline logic, I'd have to look into that.
It may not be a tree, just
Yeah, well, you can certainly do tree type stuff. Whether we can kind of bring stuff together, the semantics of that, I'm not totally sure. I'll have to take a look. So this is kind of a summary of the patterns here that you can go back to. And then the idea is that the purpose of this is that Spark is going to use these patterns to automate this stuff when we do model tuning, and that you can use any of these pieces without learning anything new. Like the cool thing is if I tell you in Spark 2.2 there's an imputer transformer, which there is, you don't need to know anything else to use it. You already know enough to use it. You just stick the word imputer in there and it works. We'll do a lab in a minute where you can switch from a really trivial algorithm to a neural network by just pasting a different name in there, basically. So that's one of the nice things. It produces a very kind of low cognitive load. You don't have to worry about the syntax. So that's maybe an advantage compared to R, where it seems like every professor that implements a new algorithm also implements some custom syntax for how to use it. So you can't really switch without knowing exactly the right call to make. And if you're bored by this, which you will be hopefully by the end of the day, then we're all winning, right? Because the idea is that this API pattern is not supposed to be complicated or tricky. Once it sinks in, you'll hopefully be bored and not care about it, and that's great, because then you can focus on the actual interesting work. So we'll come back and talk about the second set of patterns in a little bit. But I don't want to do too many kind of slides all at once. Here we're going to do a slightly more complicated version of the same thing, and the goal here is to look at the pieces we left out last time. So last time we did like the very, very minimal skeleton of building a model and doing some predictions. Here we want to look at things like tuning, cross-validation. How do we plug those pieces in to get Spark to help us tune our models? So I'm going to cruise slightly quickly through the first part of this since we just did basically the same thing. Here we'll use all of our predictors. And I'm just going to zoom. I want to focus in on just the stuff that's new. So we'll go ahead and grab the data, and this is the same thing we looked at before. We'll clean it up a little bit again by doing schema inference and reading the header row, just like before. Here you can see the result of the schema inference. So on any data frame, you can call .print schema, and you'll get a tree view of what the schema looks like. This schema is flat, so it doesn't look super tree-like. You can also see the data types, right? So now that we've done inference, we've got some of these parameters are coming in as doubles, which is a good thing. But we still have, now we've got some that are coming in as strings, and we've got to manually process those to turn those into numbers.
So this is happening automatically, that detection of
The types?
yes.
Yeah, so that happened because I did this, because I went option infer schema true. So when you're exploring data and just experimenting, this is a great way to just like save yourself some work. In production, this is not a good idea because it's expensive, and presumably you already know the schema. And if the data doesn't match that schema, you want to you want to deal with that in a certain way. So I actually have an example later where I'll show you how you can specify a schema manually and what happens if stuff doesn't match. But yeah, this is when you're just exploring and playing around. The infer schema is really handy, and this will work for things like CSV, JSON. So this, I'm going to skip over that cell. That's not so important. So what I'm going to do in this cell here is I'm going to do a couple things. First, I'm going to drop the first column in the data is a row number, which leaks data because the data set is ordered and tells us it's not real data. So we're going to drop that. That's the one that looks like _C0. So this just shows like what the API looks like. We can say drop that. Then I'm going to make another column, and I'm going to create a column called label. So I'm going to say with column label, and I'm going to define that column as being the price cast as a double.
So one question here, why do you have I'm sorry, I'm not an expert in Spark, why do you have a single apostrophe?
Yeah, no, so what's going on there is that's a Scala symbol, and it's one of the ways of defining a column. So the long way to define a column, by the way, is like if I have this, is like this would be the longest way to define a column. It would be something like this. So data.apply and then the name. So this is the long way to do it. This is what that other thing eventually desugars down to. But Scala is big on shortcuts. So one thing we can do is we can get rid of apply, and Scala always calls apply if you put parentheses there. So that gets us to there. If we happen to have a data frame, we can also put a $sign and then a string. And notice that this says column name price. So this is another way you may see it. The $sign is kind of inspired by R. It's code that's in Spark to do this conversion, but the $sign is kind of inspired by R. And then the reason I use apostrophe here is because I'm lazy, and that's the least keystrokes. You just need your pinky finger to hit the apostrophe, and you're good to go. So that's why I tend to do that. But they all get you to the same place, which is a column object. So here I'm just showing how we can give it a new name, and we can cast it, and we can throw away the old version of price. And we get some data frame that looks like this. So again, for time reasons, I'm going to skip over a couple of these things that look at like kind of histograms of some of the properties and how could I tell if I had a bunch of rows that are missing some data, because we'll look at that later. But what I do need to do is convert these categorical features into numbers in a reasonable way. So that's kind of a standard thing you're going to need to do. And Spark doesn't do it automatically for you, but it does give you helpers that give you kind of a standard pattern for doing it. So if we look at like the distinct values, say in the cut column, we've got a few of those things. And I'm not going to count them. But what we want to do is convert these over to numbers. And we're going to do that. We're going to do a kind of a two-step process for that. First, we're going to use a helper called string indexer, which is going to build a lookup table to convert these to numbers. And then, because we're using an algorithm that is kind of space and distance and direction oriented, we're going to one-hot encode them so that we don't, confuse the algorithm by having arbitrary numbers that don't have the right kind of, distance and direction. And the way we would do that with Spark is we're going to use a built-in transformer called one-hot encoder. And we're also going to use an estimator called string indexer. And I've got links to the docs here, but I'm going to manually code these and show you what it looks like. So let's see, our data frame is called data2 at this point, right? So what I'm going to do is first I'm going to make a string indexer. So I'll just do one of these, then I'll show how to automate this. So I'm going to go my string indexer equals new string indexer. I have to import org Apache Spark ML feature. So I'm going to make an indexer, and then I'm going to go set input call. So we're going to read data from the cut property, and we're going to set the output call, and we'll call that, say, cut index. And now how am I going to apply this to my data frame? Does anybody remember what's going to have to happen here? So the string indexer is an estimator, so that means I need to fit it first and then transform with the results. So I could say my string indexer model equals my string indexer dot fit against data 2. So if I run that, I should get out a string indexer model over here. And then if I want to apply that, I'm going to go my string indexer model dot transform, because remember, the estimator always spits out a model. A model is a transformer, and with a transformer we always call transform to use it. So I'm going to go dot transform on data 2, and if I do dot show, we should be able to see that here. So you can see we haven't lost any data. What we've done is we've just taken the cut, we've internally converted it into a number, and then put that down here under the cut index. So the next thing I want to do is make the one-hot encoded vector. So I'm going to go, maybe we'll comment this out. And what I'm going to do is I'm going to go my one-hot encoder equals new one-hot encoder, and I'm going to follow the exact same pattern. So hopefully it's starting to get a little bit boring. Set input call. So this is going to take the data from cut index, and we'll put this into an output column called cut vec. Now, one-hot encoder is a transformer, so I don't need to do any fitting. I can just go my one-hot encoder dot transform. And now what am I going to feed into that? I can't feed in data 2. If I try that, it's going to blow up because cut index doesn't exist on data 2 because I haven't actually run the string indexer piece on it. So this is why we have the sequence of operations where the pipeline stuff fits in. But I will do this manually first just to show you again. So I'm going to go val data 2 with index equals this thing here. Data with an A. And then I'm going to take this guy and feed that into the transform, and we'll do a show just so we can see what that looks like. And now you see we've got the same thing again, but over here on the right we've got cut vec. So a lot of times people ask, well, wait, what the heck is that thing on the right? So that's what it looks like when we display a sparse vector. That's just how it ends up looking in this view here. So Spark has dense vector and sparse vector support internally, and you can switch between them. If you display a sparse vector, it looks like this. So the 4 represents the size of the vector. This is the list of non-zero indices, and this is the list of values in those non-zero positions. So that's all that's going on there. Now, again, this gets kind of tedious. So, hopefully you're like, okay, I get it. Now show me how to not do this all the time. So in this next version, we're going to use a little bit of Scala to kind of automate this, right? Because what we need are indexers for all of the categorical columns, one-hot encoders for all the categorical columns. We want to put all this stuff together, and we don't want to write it by hand. So what I'm going to do here is list out the categorical fields here, and then use a .map. So this is very much like the Python, map call. So we're going to say for each of these fields, let's produce a string indexer according to that recipe we just used with the appropriate input column and an output column that adds index. And then for the encoders, we'll also do the same thing. So we're going to say for each field, make me a one-hot encoder whose input column is the output from the indexer, right? So the field name plus index. And the new output column is going to be the field name plus vec. And if we want to put all these things together, we can say, take a new pipeline and set the stages to be all the indexers and then append all the encoders. So the plus plus thing is just a method on sequence in Scala that says append a whole other sequence. So we'll put all these things together, and then just because of the way this API is designed for Scala, Python compatibility and R compatibility, we need to do a to-array here. And then we'll do a fit and we'll do a show so you can see what this looks like.
Can I ask a very basic question?
Please.
If I know you're using Scala in this case, if I had to use Python, I know the syntax would be different. Can I just do it like that?
It's almost identical. It's a tiny bit different.
To go you off track.
Yeah, no, it's an important question because it's it's a key piece of the Spark mission to support, like, there's lots of languages, but the most important ones are, besides SQL, are like Scala and Python. And so there's a lot of design decisions have been taken to make sure that this stuff can be done in Python in a straightforward way. And that all this stuff is supported in Python. So it's a good question. A lot of the syntax is identical. Some of the Python stuff is a little more idiomatic in terms of like instantiating like a Python object with like named fields, like pipeline stages equals, and then a list.
My question to you, I know you are using Databricks or you're from Databricks. Like you have this similar like kind of notebook thing for Python also?
Yeah. You can do notebooks in Python. We can mix Python. We'll have an example a little bit later where we actually we're in Scala, we jump over to Python to use scikit, to use scipy to calculate something and then put that number back into Scala. Okay. So they're good questions because you want to make sure that all the stuff will play nice. And you may build some extension to Spark in Scala, but the rest of your team may be Python folks that don't really care about Scala, and you need to make sure they can use your stuff. So it's critical to the mission. So it's a good question. Yeah.
So Adam, back in like I want to say it was like in the Spark 1.4.1.5 days, the coverage in the Python APIs was not nearly that of the Scala APIs for like the data frame APIs. So is there pretty much coverage parity like in the ML APIs between Python and Scala? I mean, I'm always hesitant to say it's 100%, but it's pretty close to 100%. The mission is to have 100%, and the lag is not because people don't care about Python. It's just because what happens is when a new feature comes out, it's always implemented in Scala first, and so sometimes there's a little bit of a lag. Sometimes there's like a 1-point release lag before something will catch up in Python. But yeah, the goal is to absolutely have 100% Python parity within the machine learning.
The difference between the code that you wrote and the one here, we define the different categories, like cat, color, and clarity. Is it for performance reasons that we need to define those values?
Oh, wait.
Instead of letting Spark define them by using all the rows?
Well, so Spark will not, Spark needs to be given vectors of doubles. Like you can't run a Spark algorithm over anything else that's not vectors of doubles. There are some toolkits like that will kind of automagically do that for you, or you can say like create dummies in some APIs that will automatically do all the right stuff. And you could build helpers like that, but it has to be done. It has to be done at some point and get everything assembled into a single vector for Spark. So it's not so much performance. It's like it has to be done. I mean, is that answering the question, or do you think it's something else? Or?
I think it's about the difference between the previous code and this.
Oh, I see. Between like here where I did it manually.
Yeah, here.
No, so the reason I did this was, so this is done because I basically want laziness. Like I don't want to basically don't repeat yourself kind of thing. Like I don't want to write the same code over and over again directly. This isn't really going to perform any differently. But one, it saves a lot of typing, and two, and a lot of times in real life, you may have a data table that's 1,000 columns wide, or you may have a data table that has a separate file that describes the meaning of the columns, and so you can't really, or you don't want to work with it by manually
manually handling each column. You want to kind of automate things. So you may have a task in your actual job where you ingest some file, you read a description file, you use the information in the description file to pre-process the other file. And so I want to show you kind of how you could automate that. Because you may not want to deal with all those things just directly. But the overall performance is going to be about the same. Cool. Okay, so now we've built some more vectors over here, but we're still not totally ready to go. Like, what do we need to do before we're ready to build a model on this? We need to take all of our predictors and merge them into a single long vector. So we're going to do that using the vector assembler that we used before. And that's going to look something like this. So I'm going to make a vector assembler. I'm going to say set input calls. And what I'm going to do is I'm going to say, here's what I want to feed into the input calls collection here. For each categorical field, I want to put in the field name plus vec. Those are the ones we just built. Then I want to put in this sequence where I manually list out all the other predictors. So caret, depth, table, x, y, and z. Make an array out of that. So this gives me an assembler that should produce a vector in the column called features that has every predictor in there. And then my pipeline is going to look like this. All the indexers, then all the encoders, then the vector assembler, and this colon plus is just another Scala method. So it's not a special operator. Scala lets you basically use any key on the keyboard, more or less, to define methods, which is both a feature and maybe not everybody loves it. But colon plus just says take a collection, a sequence here, and add on an item. So we're going to add this guy on. And then we're going to fit against the data, transform, and show, just so you can see where we are, because we're not totally finished yet. So this is wrapping, but if I shrink down the browser window, you can see all the way on the right, this is the final feature vector. So it's 23 dimensions long, and it's got these various non-zero elements in it. And now we want to go ahead and add the linear regression algorithm. So we can do that by just making another pipeline that looks like the one we had, and then we're also going to add on an instance of linear regression here. So this gives us this complete pipeline. And then we're going to go and do a basic model building and prediction the same way we did before. So this code is just the same as we did in the other lab. So I made a little scatter plot at the end here of label versus prediction so we can see how well we did. This is definitely a lot better than the other one, right? Because we're using a lot more information. So the thing that we want to introduce here, and I'm going to cruise through this basic evaluations piece because, again, we just talked about it less than an hour ago. So this kind of stuff we already talked about. We can see our RMSE is better. Our R squared is a little better. What I want to zoom in on is this guy here, because this is the thing we haven't done. So tuning. And in fact, what I'm going to do is let me show you the slides for this first, and then we'll run it. And that'll probably bring us just about to the break. So we talked about evaluator. And last time we used evaluator, we just used it to get a statistic for us to look at as humans. Like, hey, what's the RMSE on this model with this data? And so what we want to do now is look at using that for hyperparameter tuning with Spark. So we said evaluator calculates statistics. It generates one stat at a time where you have to set which statistic you want. And the way we're going to do hyperparameter search is we're going to add a couple more classes here. And then we'll have covered all of the key classes that we need to. So one is called param grid builder. Param grid builder is just a container for all of the different params we want to try out. And it's called a grid because you can think about it like this. For each parameter that we want to tune, we're going to have a set of test values. And Spark is going to try every single combination of those. And it will do k-fold cross-validation and pick the best parameters and the best model out of all of that. So this is the idea of param grid builder. And then I'll show you the API for it. But the idea is you just pick which params. Each param on these things has a name. Like if you take an object in the API and you type explain params the way we did before, you will get a list of the params. Some of those params are not ones you would tune, others are ones you would tune, but you can do that as well as look at the documentation. Once we've got some params, like in this case maybe it's a decision tree, we want to tune the max depth, and the max number of bins for discretization, and we want to try those values. Once we've got some idea there, we're going to go and feed it into Spark. And then we're going to use a cross-validator to perform k-fold cross-validation. And that's what's going to glue this whole thing together for the tuning. So when we make a cross-validator, we're going to wire it up to a param grid so it knows what param values to try. We're going to wire it up to an estimator so it knows what it's trying to improve. We're going to wire it up to an evaluator so it knows how to tell which version is better and which version is worse. So the cross-validator is going to be like the hub here. We're going to attach our pipeline to it. We're going to attach our params to it. We're going to attach an evaluator to it, and then we're going to say go. And it will do cross-validation by breaking up the data into pieces and running multiple training and validation passes. So let's take a look at the code for that. So what I'm going to do is import the right classes and then create param grid builder. And for each row, I mean, if you think about the grid the direction that I did, it looks they're rows. For each row in the picture we just saw, I'm going to go add grid. And I'm going to explicitly specify a parameter. So in this case, like elastic net param. So, and again, like if you were wondering, like if you go, let's see, is this guy live? I can go .explain params. So if I'm too lazy to look in the docs, I can do this. This will tell me the params that I can work with. So some of these things I might not want to tune. Some of them I might, but this summarizes what I can do with those. So here we'll just for an example, we'll play with elastic net, which is like the mixture of how much L1 or L2 regularization I want. These are the values over here. And then the actual regularization amount itself in the cost function, we'll try out these values here. And then we go .build. So this gets me the param grid. And then I'm going to make my cross-validator and just hook it up to all these pieces. So I'm going to go new cross-validator. I'm going to say set estimator, and I'm going to point it to this complete pipeline. So what was the complete pipeline? The pipeline was the thing that transforms all of our data appropriately and then fits the regression against it. So the pipeline includes the data processing and the model building piece. Then we're going to attach this evaluator. And so this is what the cross-validator will use to know which combinations of params are better or worse. Then we're going to attach the param grid we just made. That's this guy here. And then for the cross-validation, we'll say how many folds do we want in the k-fold cross-validation. I think the default is 3 anyway, but I put 3 here. And cross-validator is actually an estimator. So it composes all this other stuff, and then we go cross-validator.fit, and that will spit out a cross-validator model. Yeah, hopefully not too long. I intentionally made this kind of very tiny with just a few combinations of params so that it wouldn't make us wait here too long. Let's see, if you see where it says connecting here, if it gives you that connecting thing, it means it's having some trouble talking to the server. We can probably refresh and see if it gets happier here. I'm having trouble connecting to the server. That's not good. Is anybody else having lost connection to the server? Ah, dope. Nice. Interesting. That's fantastic. Nothing like having it blow up. Well, let's see. There's a couple things we can try here. So first, let me just make sure it's not the internet itself or something. Okay, so my network connectivity is fine. Here's PySpark. Interesting. Well, I'll see. I mean, we should be able to refresh. One of the cool things is that since all the code is really running on the back end anyway, if you refresh the front end, it won't do any damage. It just just refreshes the view. But I'm having some Looks like the front end of the server is not behaving really well here, which is not great.
It's almost break time.
Sorry?
It's almost break time.
That is true. That is true. Luckily, it's almost break time. We'll hope that this guy comes back up in some reasonable way.
Do you happen to know what is the current version of Spark offered on Amazon?
I think the latest.
Yeah, it's pretty EMR. You mean on EMR?
Yeah.
Like, EMR is pretty up to date. Like they've been pretty. I mean, I can't tell you the exact version number, but I don't think they're behind by any significant amount.
Can I ask a layman question?
Yeah, please.
I know Amazon recently announced Athena, which is basically Presto as a managed service. How would where would Spark be better than Presto? No.
So to be honest, like it depends on the query. So like there's no like I did some work with Netflix where because they use like every open source tool, and they had like some stuff that runs better in Spark and much faster in Spark, and then they had some things that run much faster in Presto and don't run well in Spark.
I would say, what would be the use case where Spark would overshine and get, what would be the thing where I would consider if I have the two flexibility in two options?
Well, so I guess there's two categories. So one is like in terms of like the general kinds of things that you can do within the same programming framework, I think Spark is broader. Like you can build more kinds of applications within the Spark framework. So in that sense, sort of Spark gives you a unified tool for that stuff. For specific queries, Presto may be faster, and the answer of when you want to use it is you'd have to actually just benchmark the query and see. Like no matter how awesome Spark is, if the query runs 10 times faster in Presto, it may be worth breaking that whole thing out just to make sure that you can do that. But this is not, so like from an architectural point of view, like Spark may be a broader platform, but in terms of like performance on specific queries or specific workloads, you just have to see. There's not like a single answer, I don't think.
On those same categories.
Okay, but we're talking about two different things. So let's just disambiguate. The question is, the main question I want to answer is, does this work for parameters that take string values? So the first thing I want to just clarify, those were properties. These are hyperparameters. They're parameters of the algorithm. Those things we're talking about were properties of the data. So it's a slightly different thing. The data values all have to get converted into doubles sooner or later, and they all have to be presented to the algorithm as a single vector of doubles.
Okay.
So that has to happen. Now over here, that's a really interesting question because this API here with these parameters, and we'll see it in the afternoon when we have to code the back end of it, is a little bit weird. And the reason it's a little bit weird is a whole little mini framework around these parameters. And the reason is to make it port nicely between Scala, Python, etc. Like if the goal was just to make a Scala idiom API for this, like a lot of shortcuts could be taken. But instead it's very explicit, like there's setters and getters, and this is actually an object, which is a parameter object, and those things are typed. So if it's a parameter object that takes a string type, then you could put strings in here. So I'll show you an example of what I mean. If we look at the decision tree, so if I go down to decision tree here, so in decision tree there are some parameters, like impurity here is a parameter, it's a hyperparam for the algorithm where you can say I want entropy or Gini impurity, right, for making my splits in the decision tree, and it's one of these params. So in this case, it's a param that's actually typed as a string param. So if you wanted to tune that, and let's say you wanted in your grid to try both Gini and entropy, you would say like my decision tree dot impurity as the pointer to the param object, and then the values would be strings that look like this, like entropy and Gini, like that. So the short answer is yes, you can put strings in there if the parameter type takes a string. These parameter types are numeric, but yes.
So maybe I got it wrong. So it is possible to have non-numeric properties or text.
It is possible to have non-numeric properties of hyperparameter, properties of your components, of your transformers, estimators, and so on. It is not possible to build, in the normal API pattern, it is not possible to build a model against data that has anything other than a vector of doubles.
Oh, okay, got it. So you have to categorize them into
Right,
numerics.
right. And I say like normal pattern because, as we're going to see in the afternoon, you can write your own estimator, and if you could theoretically write all kinds of crazy stuff in there, but you'd be going outside the norms of how the system works, so it might not be compatible with everybody else using Spark. So what I've done here is kind of run this. I imported all the stuff into this other location in Databricks so I can continue kind of demoing this. And I ran everything up to where we were so we could go ahead and try it here. And so this is where I think we had gotten to just about here, where we were doing this tuning. And then we'll go and see how things came out from the tuning. Yeah.
Question. So in this example, the hyperparameters tuning that is happening here, it's an exhaustive grid search.
Yes.
So I believe this would be very computationally expensive, and in scikit-learn I've used something known as skop, which if you give a range, let's say for any hyperparameter, and it decides based on a distribution. So do we have something similar in Spark?
So there's nothing built in. You could build things that approximate that probably without too much trouble. So for example, you could build a helper that, if you wanted to, let's say, sample from a certain distribution with it between a range, you could build a helper that generates this list by actually doing that sampling. Or let's say you wanted random grid search, so you didn't have an exhaustive set of values to try. You'd essentially have to run this whole thing more than once. But that should also scale linearly. So in other words, running, let's say picking 3 combinations here and running and then picking a different 3 using your random selection and doing that, say, 4 times, a total of 12, should take the same amount of time as just doing this with 12 to begin with. So if you wrote a helper that basically ran this more than once, you should get the same performance. It's mildly annoying that stuff's not built in, but then again, it's open source. You're welcome to contribute a design doc to it. But yeah, no, seriously, I know what you're saying, and that is a common question. So yeah, it's you can build that without too much trouble, but it's not built in. Cool, okay, so this thing has finished here. What is it actually telling me? So it's spitting out these various combinations. And there's 2 things I want from cross-validation, which is 1, what's the best model? But 2, is there a difference in performance between these things? Because some may be more expensive than others. So here's how we can do that. When we do our cross-validation, we get out a cross-validation model. If I call .average metrics on it, what I'm going to get here is 1 entry. So what this is for each combination of parameters, I'm getting the average across the k folds, right? So if there's let's say I have 2 parameters, 2 combinations each, that's 4. And if I'm doing 3-fold cross-validation, that means for each of those 4, I'm running 3 trials. This is the average of the 3 trials for each of those 4 configs. And the statistic that's being shown is whatever my evaluator was set to. So in this case, RMSE. So this is handy, but the next question people ask is, well, great, which one goes with what? How do I read that? So they are in the same order as the result that you get if you do this. If you go cvmodel.getEstimatorParam_maps. So what this is a summary of the different param combinations that were fed in, right? So this is, you can see what we put in. This is ElasticNet 0.3, regularization 0.1. So these are all the combinations. So if these guys, if the performance numbers, the average metrics, are in the same order as these guys, we can zip them together using a Scala zip that's very much like Python zip. And then we can sort them out. So what I can do is I can say, okay, get estimator param maps, and the one I want, the map I want, is the one I get by doing a average metrics zip with index and then finding the smallest RMSE. So this is just, you could play around with this. It looks a little bit weird the first time you see it, but all I'm really doing is saying, I want the index of the best performing one, then get me the param map that goes with that index. And so this is how we can find out what params actually performed the best. Now, if you just want the best model out, it comes with one built in. Like if you go cvmodel.bestModel, that model is the result of finding the best params and then training on all of the training data. So, which would probably be the next thing you'd want to do. So the cross-validator will do that for you. You can just go best model. But if you want, but a lot of times you want to see, like, is there a statistical difference between the best and the worst? Like, am I getting anything out of this? So that's why looking at the actual. Sorry. Yeah. So that's why I would want to look at these numbers here.
Do we have an option to define our own performance matrix? Let's say MAP, which is not defined.
Oh, you mean your own evaluator?
Yeah.
My gut says yes, but I haven't actually done that, so I just want to put a little asterisk. Let me take a look. I mean, if you're willing to hack on Spark, you can do anything. But when I say maybe is because depending on sort of how let's say your company has a deal with a Spark vendor. There may be rules about not going and hacking the internal classes. So when I say maybe, I want to see whether all the APIs are public. There are some useful APIs in Spark ML that are not public. They're not publicly accessible APIs, so they're harder to work with. So let me just take a look at that. My gut says probably, but I can't promise. Okay, so we've seen how we can do cross-validation, how we can set up parameters we want to try, and how we can get Spark to use an evaluator and figure out which are the best parameters for the model based on our evaluator. The rest of this stuff here is very similar to what we did before, so again, for time reasons and so as not to bore everybody, I won't go through all these. You're welcome to go through these on your own and kind of take a look. This just walks through the same calculations we did before. So if Community Edition is running, we can do a nice little lab here, which is fun. If it's not, we can't. So let me just see if this is alive. It doesn't look alive. So what I'm going to do is we'll just leave that thing. So what we could do, and if we have time, maybe we'll come back to it, is there's a neat lab based on a notebook originally published by Databricks where they use the MNIST digit data set and build a decision tree over it. And then the cool thing about the lab is that you can swap in a neural network for the decision tree, based on what we know now, by basically just changing one symbol name and then doing one tiny little adjustment to the data that's really an artifact of the data and not the Spark. And so that's a fun lab to do. But we can't do it now because CE is broken. So we'll come back to that. If we run out of time or you end up not coming to the afternoon session, the lab discussion is in 05 lab tree versus ANN, and then there's a solution right here. So maybe we'll come back to that. In the meantime, what I'll do is I'll just cruise on here into Notebook 21, this one that says features. And what we want to do is we're going to play with the airline data set that you've probably also seen before at some point. But we're going to look at doing things like, things that are maybe a little bit trickier or not as obvious with the basic core Spark API, including sorting out schema and dirty data and stuff like that. So the data, let's see, let me make sure I connect to the right. I'm going to use this cluster here. So the data lives under here. Let's get this guy spinning up. And then we know how to read this now. We can do a spark.read, header true, infer schema true. And this will get us something, a parse is OK. We're going to call this data frame raw. And it looks like this. So this is just for anybody who hasn't seen this before, this is a small slice of a publicly accessible data set that has a ton of statistics about domestic flights in the United States. And so for each flight, there's all these different properties about how the flight was scheduled, how it actually ran. Some of the data is clean, some of it is broken, like for example over here where there's delay and diversion information. There are no clean records at all in this data set. It's completely broken. So this is kind of real world data. And we're going to play around with a little slice here. So the first thing I did is I read this thing in and I used infer schema. But since this is a real data set and it's dirty like the real world data often is, there are problems. One way to see the problems is to do print schema and just do a sanity check. Does this thing look right? and it does not look right. So some of these things look good, like year is an integer, but then we have these things. Departure time, this should be a number and it's coming in as a string. What does that mean? It means when Spark looked at the data, somewhere in that column was something that was a string but couldn't possibly be a number. Right? Now luckily we can figure out what that is and we can fix it, but this is one way you could see it, is do something like this. Another way to tell is if you did a .describe to get column statistics on this, any column that doesn't have a numeric type is not going to show up in the describe statistics. So if you look in here and you're expecting to see stats for arrival time, of course I should actually display it, but in any case, if you look in there at the columns that show up, they will only be the ones that were numeric. So once we discover that there's a problem, we can look at how to fix it. So one way to do it, like brute force, if you really have a messy data set and you have no idea what junk is in there, is to actually start going through and like writing filters to look for stuff, like selecting things that when you cast them to a number turn out to be null or something like that. In this case, if we explore a little bit, what we discover is the main issue is that they use the string NA for data that's missing, right? And luckily Spark has a built-in helper that can convert an arbitrary string to nulls or nans if you tell it what that string is. The downside is that it's not obvious in the docs. And the reason is because the reader framework, so the thing that lets us say spark.read.csv or spark.read.parquet or spark.read.text, that data source API is pluggable. It's public. You can write your own pluggable data sources. The downside is that it's generic, meaning any data source can take any options that are meaningful to that data source. So the Spark data source API doesn't understand any options. It's the CSV reader code that understands the options. And I don't think that's really documented anywhere specific. So I went down to the source code. This link is the current source to csvoptions.scala. And if you look in there, you'll see there is an option called null value. And that's the one we want. So the good news is there. The bad news is you have to dig a little bit, but not too hard, not too deep to find it. So this is going to say anything that shows up as the string NA treat as null. And we'll go and try this again, and we'll call the result cleaned1. And we'll print the schema on that to see if it fixes things. So if we look through here, this looks pretty good, right? We've got all of our integers. Unique carrier is supposed to be a string. Tail number is supposed to be a string. Airports are strings. Cancellation code. These guys here at the end, this data is all junk anyway, so I'm not going to worry about that because we're going to want to get rid of that. So this looks pretty good, right? Why am I interpreting it that way? Because if I had, let's say there was some other dirty data in there that wasn't either a number or the string NA, then it would still show up as maybe a string or something else. So this tells me that just taking care of the values marked NA was enough to get reasonable data into those columns. So we can take a look at that. It's actually going to look the same because I don't think there were any corrupt data that we could see in the first few rows. If you scroll over to the right, which sadly you can't since I know your instance isn't running, you can see the effect here. Like these were NA before, now they show up as null. So if we wanted to kind of investigate what would happen, if we wanted to kind of investigate the characteristics of broken data, we could go in and kind of figure out how many rows are broken and all these other kinds of things to figure out what to do next. In this case, we're going to cheat. I happen to know that almost all of the rows are okay, meaning there's like only a couple percent. If we assume that those couple percent don't hide our awesome information, we can just kind of drop those, and we'll look at how to do that. I'm going to skip over that piece here. What I want to do is look at processing data using a manually specified schema. So data frames in Spark all have a schema, some kind of a structure to them. Even if we do infer schema, they end up with one. And the schema is a public member on the data frame. And it's of a type called struct type here. So this looks really messy, but that's just because there's so many fields. Struct type is really simple. You can make a struct type out of a list or sequence of struct field objects, and a struct field just has three things: the name of the field, the type of the field, and whether it's nullable. So making a schema programmatically, we could do something like this. So let's say I've got this, and just as a demo, let's say I want to specify the schema manually. And I'm going to do two things. One is I want to drop the last 6 columns or whatever. I know there's nothing good in there. The other reason I might want to do this, especially in production, is it's much more performant, right? Because Spark has to do a lot of work to do schema inference, especially with JSON, because you can have lots of different documents that don't match, and Spark will come up with kind of a union structure that fits for all of them. So if you're getting data in CSV or JSON in production time, you probably want to specify a schema, and you may not want to key that all in by hand, right? You might want to automate it, because again, your company, you probably have a description file somewhere that says what the fields are supposed to be. So you can automate that by using this struct type and struct field classes. So this is what it would look like to create a schema. Here I didn't automate it. Here I just manually typed it out. But you could see how you could if you had a dictionary of like names and fields, you could just automate generating this thing. It's a plain old object. There is a Python equivalent to this that looks a little bit different. And I've just said struct type made of a list of struct field, and then I just listed out all the fields that I wanted, and then the types, which are under that package here. And then I marked them all as nullable. And then what I did is I just threw away these other ones. So once I have a schema, so I have to evaluate that. So once I've got a schema object, the way I apply it is I go like this. Instead of saying in first schema true, I say dot schema, and I pass the schema. Now here's the interesting catch with this. The whole point of this is to have a strongly typed structure and not have Spark spend time like seeing whether it's true. The downside to that is Spark has taken my word for it. If the data doesn't match this, as soon as I do a calculation that requires this to work, it's going to blow up. Right? So that's kind of the double-edged sword of doing lazy evaluation on big data sets. So now at this point, Spark is going to say, okay, cool, I believe you. Right? So it has a schema. You can see a little bit of it over here. Spark is saying, okay, I believe you that this schema is there. So you've got a data frame. What do you want to do with it? So I could come in here and say, okay, well, I want to count it. Now, just to give a, let me just give, just to make that point a little bit more real. If I cut this out, so what I'm doing is I'm running the same command, but without the null value thing. If I count this, okay, that works. The reason it works is because you can count rows without actually doing any type analysis. This is one of the nice benefits of that data frame engine. Is data frame is smart enough to realize that it can do various calculations without touching lots of the data. So it can count the rows. If I ask for a correlation between departure delay and arrival delay, which might be an interesting thing, it blows up, right? And you can see the reason for the failure is in here. Number format exception, input string NA, right? So this is what would happen. And this is the reason I mention this is because it could be the two different groups in your company. Like one group is doing one part, and you're like, okay, cool, I've got mine. The next person's getting that data, and like, hey, this is blowing up. So this is lazy evaluation can kind of cause those things to happen. So I put this back. That will put nulls in there. The nulls are kosher for computation. So now this will actually work. Okay, so now that I've got this, let's say again, I'm kind of cheating because I know that there's only 3,000 or 4,000 rows out of 200,000 that have any problems. Let's say I want to get rid of them. You can do those things with filters, but there's a handy helper object called dataframe NA. It's dataframe NA functions. I'll show you. It's right here. Dataframe NA functions. So from any data frame, if you call .NA, you get an instance of this thing here, which allows you to do stuff like drop, fill, or remap data. Right? So this is really handy when you want to go and just swap out data that's not kosher. In this case, I'm just going to say .na.drop, and that's going to give me a new data frame that only has the valid rows in it. So this gets me, and I think these guys are all good at this point, at the 196,000. If we come in here, we can see the list of columns. And so let's say we were actually going to do some modeling exercise on this. Like the goal of this notebook is not really to produce a great model about airlines, but let's say we were wanting to do this, we might want to get rid of some of these columns. So some of them we might want to get rid of year because there's only one year that's here. We might want to get rid of these other ones because they're correlated to the stuff we're looking for, right? It's like if I know the air time and the departure delay, I can probably predict the arrival delay, but that's not really legitimate. So if I want to get rid of these columns, how can I do that? I can make a list of the columns. Unfortunately, in Spark, the call to drop won't take a list of string columns. So I thought this would be a fun excuse to show a neat Scala trick. Scala has a pseudo kind of a splat operator that you can use in a case like this. If the API requires separate parameters and you have a collection because you're processing things programmatically, you can use this : star thing. And that will actually get you what you want. Because the API itself, which lives under data set here, so if you're trying to figure this out and you're like, well, let me look up the data, let me look up the API. These are the APIs for drop. So there's drop that takes a column object, drop that takes separate column names, that's the one I'm trying to use, and there's drop that takes a single column name. Right? So none of these are quite what I want, so that's why I did this. So I can programmatically have a collection of columns and just drop them all at once. And then those hopefully are gone. And now we can go and do, yeah.
Underscore splat is a Scala syntax, yes?
Yeah, there's this : star, and it's not like, I'm not a Scala expert. From what I gather, it's sort of, it's not exactly meant for this purpose, but it maps mathematically to the same thing. Okay. Probably the best way to say it. Okay, so let's see. The next thing we might want to do here is, let's say we want to impute data for a column that has like bogus data. In the past, I used to say, well, this would be like and we'll actually build a transformer that does this in the afternoon, and this used to be a pretty realistic use case because you always need to impute data, and Spark had no built-in support for that. In 2.2, I'm pleased to say there is going to be a transformer, I think it's transformer, that's part of the API that does imputation in the sensible way, pretty much exactly what we're going to do it. And the other good thing is now you can, after today, you'll be able to say, cool, I pretty much wrote the same code. So now I'm like, I've got all that under control. The downside is this will be a less interesting exercise in a few months because it's built in. But let's look at the taxi out column, right? So this is how long, I guess, the plane took to taxi from the gate to the runway. There's 32 records that say 1 minute. I don't know if that's legitimate or not, but let's pretend that that couldn't possibly be true at some big airport, that the taxi out time is 1 minute. We think that that's no good, and we'd like to impute some other data there rather than throw these rows away. So what we're going to do is we'll start by writing a function here to figure out how to do that. In the afternoon, we'll bundle that up into a transformer so that other people can use it without learning our weird API that we're inventing right now. So how can we do this? So what I'm going to do is first I'll just go through step by step, and then we'll try and wrap it into a function. So what I'm going to do is first I want to figure out what is the mean value, like if I want to impute the mean value for this column. So I'm going to select the taxi out column, but there is no built-in operator on a column that says get me the mean. Right? There's summary statistics. I could kind of yank it out of that in a weird way, but maybe probably a more proper way to do it is say I've got a column of numbers. Let's go and actually just treat them as numbers. So what I'm going to do is use this thing here. This is new. Well, it was officially added in Spark 1.6, but they didn't really get it officially, they didn't really plan to sort of make it for real until 2.0. So let's just put it that way. But as of 2.0, we can use this typed dataset API. And we can lazily say, I would like to treat these records as some other Scala type. So this is something that doesn't really map over to Python. You don't really need it in Python, but it doesn't really exist there. And the cool thing about this is that Spark it doesn't require physically redoing anything with the data. It really just exists for the human consumption or the view of this data. You could say that I would like to treat this as a record of a particular actual strong type, and Spark will automatically map it based on the structure of the type and the field names. So you don't have to write any metadata, you don't have to do any declarations anywhere, you can declare the classes on the fly and remap them, and it'll all just work. It's really neat. In this case, I'm just saying I want to treat this column of rows as integers. Once I have a column of integers, I can then convert them into an old school data structure, this RDD, or resilient distributed data set, which will also be an RDD now of ints, because those are strongly typed over, say, Scala objects, and then I can call mean on that. So this is just one way to get the mean value for the column. And then the fixed version, how am I going to do this? So I'm going to say something like with column, and then I want to have a condition where I say, well, if the taxi out is this bogus value, then use the mean I've calculated, otherwise use the existing one. So the way that looks in the DSL, or the data frame language here, is use this function when. So I'm going to say when the taxi out column matches 1, and I'm using this triple equals method here, then use the mean, otherwise use the value that's in taxi out. So this is cool, but if I'm you, I'm thinking, well, how was I supposed to know this was there? How would I ever figure out where this stuff comes from, right? So you definitely want to, at some point, familiarize yourself with this object here. So this is called a package object, but you can think of it as just a bunch of helper functions. All of those functions that your favorite database has built in terms of string manipulation, math, date and time arithmetic, all those things that you have to do, you don't want to write the code for, they live under this object here. So org Apache Spark SQL functions. So if you import that, and I did that, I kind of slipped it by you right here in the notebook. If you import that, you get all of these. There's about 200 or more functions in here that can do everything. There's everything from statistical functions like correlation. There's restructuring and reshaping functions like collect, list, and set. Here's some more math stuff. There's JSON processing. You can do explode, like remap collections into multiple rows and multiple columns. You can do date and time formatting, parse formatting, date and time math, all that stuff that's like not exciting, but you've got to do it, and you don't want to write it. Most of that stuff is probably already here somewhere. So like it's really useful. Like if it's not obvious, go here first before you worry about writing it or downloading it or something. Okay, so that's where like the when and the otherwise stuff is defined, and then once I've got that kind of trick figured out, I can say, okay, well, once I've added this new alt column here, I'll call that fixed 1, and now let's see what happens. So what I'm doing is calculating the mean, which is 16.6 minutes, then I'm imputing that for all the taxi out equals 1 rows, and then I'm checking to see how many rows got replaced. And it looks like there were 32. I had 32 of these before, so that looks like hopefully they're the same 32. It all matches up. So okay, so now I've done kind of the raw testing of the logic, so let's wrap this in a helper function. So this is just basically Scala syntax. I'm going to say define a method called impute with mean. There's a data frame that comes in, the name of a column that I want to be working on, the missing value, and then an output column. And what this option, so I want this to be an optional parameter, and Scala has this pattern of an option object, which is it's a placeholder for an object that could be present or could be missing. So Scala people think of this as being a container like a list, but it has either 0 or 1 thing in it. That's the best way to think about options. You treat it like any other collection. It's just the collection either is none, which is empty, or it's one of a particular type. So that's what this is. I'm saying output call is an option of string, and it defaults to none. And then I just stick my same logic in there. So I'm going select the column the client has specified and cast that to a double, in this case double instead of int, because I want to be more flexible, calculate the mean. Figure out the output column. So what I'm doing is get or else is a way of dealing with an option. So if the option has an object in there, you're going to get that. If it doesn't, it's going to trigger the or else part. And so what I'm doing is I'm saying if the user doesn't tell me where the output should end up, I'm going to generate an output column here. So the output column is going to be called imputed plus some timestamp just to get a quasi-unique kind of value. Then I go and do our with column thing with the when and the otherwise. And then at the end, what I'm doing is I'm saying if the user didn't give me a column for the output, then I want to replace the old column with the new one. So I'm actually going to drop the original one and rename the new output to the old one. Otherwise, I'll just return the data frame with both columns, the original one and the output. So here I've just bundled this together into a method. Does this more or less make sense? I know if you're not like a Scala person, the syntax might be a little bit weird, but does it seem vaguely sane? Trying not to do anything too crazy here. And then now we can call it like this. So I can go, oh, cool, impute with mean, and I can just give it a data frame, a column, and then the value I'm worried about, and we can go and get something like that. So in the afternoon, we'll look at bundling this into a transformer, which would be kind of the proper way to do it, and making it a little more flexible. So for example, maybe we don't want to just look for the value 1. Maybe we want to look for anything that's null or nan or something like that and swap in the right data. So we'll revisit this, but this is just kind of looking at how we can put these pieces together to solve some problems that are not directly in the API. Another fun thing that we might want to do is get like a covariance matrix, right? So this is like a standard thing that you would probably want to do with any kind of data that you're trying to understand, and it's not surfaced in the modern Spark API. So there's a way to do it, but we need to kind of dive into the old API a little bit to do that. So I figured I would show you kind of a recipe for doing that. So first what I'm going to do is drop the string columns from this data frame, just because that for, I don't want to convert them to numbers right now, and for the covariance matrix it doesn't make sense to have strings. So what I'm going to do is drop the origin, destination, and unique carrier, and then make a vector assembler. And notice what I did here for the set input calls. In the previous examples, I was typing stuff in, but again, programmatically, you probably want to do this without typing things. So any data frame has a .columns field, which gives you the string column name. So I can just say, oh, I'd like the input calls to be without string columns, .columns. And then the output will be called features. We'll go ahead and apply that. It's going to get me these features over here. So now comes the part where we need to use the old API. So this is not super hard, but there's two reasons why it's worth looking at. So one is there's two packages that are in parallel. Probably the easiest way is I can show you this live. So if you punch in, say, vector. So there's two different packages here. This one, org Apache Spark ml.linalg. This is the modern version. Then there's this one, org Apache Spark mllib.linalg. This is the old one. So there's nothing intellectually tricky about this. It's just you got to be careful which symbols you got imported, because the classes have the same names, right? So that each one has dense vector, sparse vector, vector, and a vector's helper. And they're not compatible with each other, although they are converters. So you just have to think, if I'm working in the data frame world, that's ML. If I need to use something from the old world, that's mllib. I can bring them both in, but I may have to alias the classes when I bring them in, or just spell out the whole class name, just to make it really clear what's going on. So I need to do that. And so here's how we can do that. So I'm going to import these old school vector, then an old school class called mlutils, which will help me with the conversions. Then I'm going to import distributed.row matrix from the old package. So what's distributed row matrix? It's basically it's treating a RDD of vectors as a matrix. So it's distributed. It's rows because we're thinking of each vector as being a row. And it's just, it doesn't really do anything. It's just a way of thinking about a bunch of vectors as a matrix instead of a bunch of vectors. It's just for convenience. And then the actual matrix trait here. I think that's a trait. And then what I'm going to do is I'm going to go mlutils convert vector columns from ml. So there are helpers for converting. It's just we have to realize when do we need to use them and sort of how do we get the right pieces in. So I'm going to go convert vectors from ml. And where am I going to get those from? Well, I'm going to take my previous data frame that had the vector, and I'm going to select the features column. And I'm going to ask for that particular column. So this is where the ml vectors live in the data frame. So then this is going to, here I can show you what this looks like. If I comment this out, we can see what it looks like up to this point. To make it kind of more step by step. So if we do this, we get a data frame that has just these features as old school vectors. So then if I go .rdd, And again, I'm going to comment that last part. Now what I get is I've got an RDD of rows, but in those rows, I should have vectors of the correct type. So how do I get those out of the rows? I'm going to go map, and I'm going to say for each row, I'd like to call get as vector, and that's this old vector here, on the first field. This is a weird and awkward API. It's rare that you need to do this, but it just kind of is how it is. In terms of inspiration, if you're just like, why would anybody come up with this? It does resemble a little bit some of the old-fashioned like JDBC, like database APIs, where it's like you've got a row from a database, and you know the order of the fields, and then you want to kind of figure out what type they are. So there is a little bit of a precedent for it, but and there are shortcuts for common types like get as int or get as string or whatever. But what we're saying here is do a conversion, get me an RDD. From the RDD, take each record. For each record, I want to pull out the 0th field or the first field, and I'd like to convert it into or cast it to a vector. So that gets me a bunch of, in fact, if we do this whole thing, you can see it will get me a RDD of old school vectors. So MLlib meaning old school here. So now I've got an RDD of vectors. Now I can just plug and chug in the old API. So I'm going to take those bunch of vectors and say, hey, I'd like to treat this as a row matrix, which doesn't really require any computation. It's just a wrapper. When I say it doesn't require any computation, what I mean is it doesn't launch any Spark jobs. Spark jobs are when Spark schedules work across the cluster in order to actually physically move data and produce a result. Obviously, something's being computed here, but because there's no Spark jobs, it's just the driver manipulating objects. We're not really moving data yet. Then down here, yeah.
Depending on your function, Spark will automatically invoke Spark jobs.
So yeah, so that's kind of that's a complicated question to answer. The short answer is yes. So you do not have to you can manually run jobs using sc.runJob, but you never normally do it. Normally you write what you want to write, and Spark will generate the jobs that it needs to. That's kind of the simplest way to say it. Some jobs are super lightweight. Like if you look at a Parquet file, it has a header. So Spark will launch a job because it has to touch the data on disk to read the header, but that's all. If you compute something like filter certain rows out of a Parquet file, that's going to be kind of a standard distributed job. And then on the other end, let's say we're training a logistic regression model, Spark might launch 100 jobs because each step in the training is going to be a job. Right. So, and you don't have to worry about those. So to actually do the covariance matrix, that is built in once I'm in the old API. So I can say matrix.compute covariance, and at that point, I'll be in pretty good shape. Notice that I'm launching some jobs for this. And now I've got this matrix back. And it's getting truncated here. If you wanted to kind of see the full thing, you could say .toString and tell it to truncate much less. That will give you a big ugly mess like this. And then if you want to go ahead and see the actual matrix in some prettier format, see if I can select this in Firefox without messing it up too bad here. If I copy this and paste it into Sublime, let's say, if I shrink this down, it will eventually line up into a nice matrix sort of shape.
You can paste it if you have Excel.
I have to turn, I could do, I could paste it with Excel, or I could just turn word wrap off. Where is the turn word wrap off?
That made it worse.
That did. Yeah, what's going on here? Okay, you know what it is? I've copied this thing out of the copy paste works differently in Firefox from Chrome, so I've messed up extracting the data from here. But you get the idea. So it's modulo the format. Here, this is the matrix. You have to take my word for it. It does actually line up with tabs and into nice pretty columns if you format it right.
Can I just, you can just clarify here. So essentially what Spark does is, right, for any ML or statistical functions, you take your raw data, and if they are categorical and text, convert them into double numbers, and then you apply the various transforms and get your insights. Correct?
Yeah. In a nutshell, yeah. You have to do all those things, yeah. And then you may optionally add more steps, but yes, right. Yeah, absolutely, yeah. I think that's like, kind of A to Z. Yeah, no, absolutely. Yeah, so this is, I apologize for the formatting issue here, but you get the idea. It is formatted and it is a matrix. So this is how we would do that. That may be exposed. I have to look and see. I've got a list of updates for 2.2, and they may be adding that to 2.2. So the need to do this little sort of dance here may go away, but I have to take a look. So here's another thing we might do in terms of feature selection. This is just kind of a demo. There's nothing, this is not a terribly difficult API to use because it is supported in the modern one, but it's another way of looking at features is there's a chi-square test feature selector built in. So you could, that tests the significance of a particular feature versus the response variable. Like is there any kind of relationship there? So that using that is just a standard estimator style. So we're going to say new chi-square selector, and we could say, oh, I'd like the top 5 features in terms of their significance against the response. The features column lives here. The label column lives here. And remember, these guys already have to be in vector form, like you were just saying. So they're in vector form here. The label's here. And then where do I want the output? And then I go selector.fit, and then I can go transform. And what I'm going to get here is another column. So this last column on the right, this guy here, is the selected features. So you might say, well, wait a second, what were those again? So if you ask for selected features, this will tell you which features by position in the vector were the most significant. So these are the ones that were kept.
Can you just go back one second? So you did the transform and then?
So what I did is I instantiated an estimator,
Right.
configured the parameters on it,
Right.
called fit with the estimator, because it has to look at all the data to compute the results. It then returns a chi-square selector model. That's what this CSM thing is.
Right.
I took the chi-square selector model and said dot transform on the data set, and that gave me a resulting data frame which added a new column called selected features. And it looks weird because of the wrapping, but that's this guy over here on the right.
Okay.
And then I said, well, this is handy, but I'd like to know which of these features, right? There's like 0, 1, 2, well, actually they're here. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 features. Which ones were picked? And so then I went down to see if I can scroll this guy. Oh, it's not scrolling. There we go, a little Firefox bug. So then I said selected features, and this tells me which particular features were picked.
So in your estimator, it's figured out these are the 4 features which are the most significant in the chi.
Right, exactly. According to chi-square test, there's also like PCA. Like we're going to look at that in a bit too. Like there's other ways of picking out. So we'll look at like PCA. But this is just one thing you might do to pick out features.
It's a feature extraction.
Exactly. So here's another one. This is a good example that like dealing with skew. This is a nice example because it shows how we can integrate. You asked about mixing Python. It also shows how we can kind of mix in Python and SciPy right into here to solve a problem. So if we look at the taxi times, so here is a histogram of the taxi times. So we might say like we might say, well, I don't like the skew here, or I don't think this is my algorithm's not going to be very efficient on data that's this skewed. I'd like to do like a de-skewing transform and see if this helps, right? So maybe I want to do something really straightforward like the Box-Cox de-skew, which is, it's been around forever, it's really standard and works pretty nicely, but it's not in Spark, right? So what I'm going to do is I'd like to use the version in SciPy, but then I've got the other problem, which is SciPy isn't distributed. So the question is, I've got a huge distributed data set. How do what do I do, basically? I could re-implement all of Box-Cox in Scala, but I'm lazy. I don't want to do that. It turns out that like Box-Cox implementation is pretty trivial once you know the lambda value, right? Calculating the lambda is a little bit trickier. So what I'm going to do is I'm going to sample from the data, use SciPy to calculate lambda in Python, and then create a function in Scala that uses that to do box cox over the full data set on the Scala side, right? And so that's fair game. I can mix this up as long as the downsampling doesn't screw stuff up. Like as long as my sampling isn't skewed differently from everything else, then the whole thing goes out the window. But
so what does it do? It does the standard deviations, and then certain things which are out of the standard deviation, it just filters out of your set or something.
the box cox transform.
Yeah.
No, well, there's a couple of cases, but basically what it's doing is it's doing either like a log or an exponentiation
Okay.
of a particular power based on the characteristics of the original data,
Okay.
to try and come up with something that looks more like a normal distribution when it's done.
Okay. And then
So-
it chops off
It doesn't chop anything off. You'll see the formula. It doesn't chop anything off. So there's an article about it. If you want to read more about it, there's an article about it here. Where you can drill down. It's in the notebooks. You don't have to write this down. You'll have the notebook. So you can, if you want to read about read about that here. So what I'm going to do here is how am I going to see this thing over in Python, right? So in Python, I can't take a Scala variable and somehow just see it in Python. But what I can do is I can put an entry into the Spark catalog, and I can see that in Python. So this is a really handy trick. If you need to move stuff between environments, between R, Python, and Scala in Spark, it's hard to move the actual data, especially because data is distributed. If you had it all local, even that would be tricky, but it would be different. What I'm going to do is I'm going to put an entry in the catalog by going create or replace temp view. So now I have this table that Spark knows about called with_vec. Now I can run Python code. So here's Python, and I can say spark.table with_vec just to make sure it's there. Right? And so now Python sees it, right? And I didn't move any data. It's just now Python has a handle to the same data. So now what I can do is I'm going to come over here into Python. So I'm going to go %Python. I'm going to import box cox from scipy.stats and bring in numpy. I'm going to grab a hold of this table. I'm going to downsample it so I can run something locally in Python. Right, so if I do a collect is one of those kind of classic no-nos in Spark because collect takes all of the data and brings it into the driver. So that will usually get you a max result size error first, then you'll go and change your max result size, then you'll blow up your driver. So generally you don't want to collect that, but what I can do is I can sample down, in this case to 5%, and collect the sample. Then I can call box cox on that, and what I want is this, the lambda value from the box cox formula, which I'm going to use in a minute. And I'm going to print that guy out, so I can do this. Right, so the lambda for this data set is minus 0.289. Now I can hop back over here into Scala.
Oh, cool.
And I can define a custom, so this also demonstrates another thing we haven't seen, defining a custom function that works over columns in a data frame. Right, so for various reasons we don't have time to get into, you can't just take a regular Scala or Python function and run it directly over the data in a data frame. Because remember, in the data frame, notionally, they're language neutral, it's just bytes. So we need to provide Spark a way to convert from that into a native type of some language we have and then apply a function that we've defined in a language that we're using. And the way we do that is by going spark.udf.register. So what this is saying is I want a function I can apply to a column in a data frame. This box cox thing on the left is the handle to that function. The string over here is how it's going to appear in SQL. So if I write this function, you can actually come in, or a coworker can come in through a totally other interface and actually use this in SQL.
You're registering your UDF as box cox?
Yes.
Okay.
Yeah, so I'm creating my own, and what it is it's going to implement the box cox transform using this lambda value here.
Okay.
So I'm going to go spark UDF register. I'm going to give it the SQL name box cox. And
Can I ask you one thing? Just
yeah.
now you hand-coded the lambda is 0.289 something.
Mhm.
How would if I have a full automated flow script, how would I just get that Python data into the Spark?
There's a few ways to do that. Honestly, I'm not sure what the easiest way to do it is. I mean, for big data, it's kind of like what we did around the back. Like you have it, you don't touch it, you just kind of get a handle to it through the catalog. For something small like this, I'm going to have to think about what the easiest way to do it is. I mean, you can write it to any kind of storage, like a memory mapped file, and read it back.
Yeah, so the easiest way is just create a new data frame and add it to the catalog.
For big data, yes, but you asked specifically about lambda, which is a single double. You could do that, but it probably doesn't make sense to go and you could do that. You could parallelize this to make a parallel data set of this thing, make a data frame from that, then in Python go and read back the row and convert it back to a double. But for something small, I'm thinking it probably makes more sense just to throw it in a space in memory where you can read and write. But to be honest, besides like writing into a file or a memory mapped file or something like that, I have to think about what's the easiest way to bridge between those. Once I've got this number here, so what I'm going to do is I'm going to write a Scala function that treats my columns like Scala values, and then the UDF register is going to make those work on columns that aren't Scala. So my function says, given lambda and given some data number, I'm going to say if lambda is 0, which in my case it's not, but this is the formula, take the log of the data. Otherwise, take the data to take the exponent of data to the lambda minus 1 and then divide by lambda here. So what I've got now is this UDF like so, and then I can apply that to the data frame by calling it on columns. So there's one more little trick I have to do here, which is taxi out is a real column. But the problem is lambda, which is a parameter to this is a number, not a column. So I'm going to use another helper called lit, and what lit does is it takes a literal value and makes it into a column of the appropriate mapped value. When I say appropriate mapped value, what I mean is columns have types that are more like database types, like they're not language specific. So in this case, it's going to turn a Scala double into a whatever the appropriate generic data frame type is for that. So I should be able to run that, and now we can take a look at the d-skewed histogram, right? So we get something like this. So that looks a lot better. So again, this may not solve like all of your problems here, but it's a kind of a good illustration of how you can plug stuff together. It's not like I had to write a whole bunch of code here, but it shows how you can actually do a lot of stuff that's not super obvious in the API, but you can kind of move things around and bring things together to solve these problems. Cool. Let's see. I guess we should do some PCA stuff. I'm just looking at the time, but yeah, let's take a look at this. So let's say we want to find principal components, right? So this is a common thing we might want to do, and I'll show you kind of the easy way and the hard way, and like why you might want to do it the hard way. So the easy way is scale the data and then use the PCA estimator that's built into the API, right? So that would look something like this. So what we would do is take standard scalar. Say the input column, those vectors live here. We want to put the output under scaled features with standard deviation and mean scaling. And then we'll go fit, and then we'll go transform. And we should get everything scaled and centered over here. And then to use the modern kind of built-in PCA support, we would just say new PCA, set input column, set output column, how many features or dimensions do we want, and then fit, and then transform. And again, that's going to pretty much get us just going to spit out the answer. So, so this is what our principal components look like. So if I can do this, why would I ever want to do something else? Well, the problem is that this doesn't perform well on certain shaped matrices. So if your matrix is wide enough, then we're going to have problems with that. So there is an implementation. Yeah?
The question is, what's too wide? Where's kind of the rough state? Like how many features?
Honestly, I don't have a good benchmark for that. It depends. It depends, but probably not as much as there probably is a good rule of thumb. I just don't know it. It's going to depend on things like how big your cluster is and what's acceptable performance. There's always that. But in terms of the curve, like if you're thinking like at some point is there like sort of a pivot in the curve where it like things really degenerate for memory reasons or for whatever else. I wish I knew that. I don't actually know that. So that would be might be in the mailing list somewhere. But it is known that at some point for matrices that are not unreasonably wide, but that you might actually come across, that the performance will degrade in this newer implementation. So I'll show you the way to do it using SVD. So that like the math of that's not a big deal. The problem is SVD is only in the old API. So what we want to do is we want to go through the same kind of thing. We're going to get this data into an old school matrix and then just call the old school singular value decomposition, that will do it for us, and then we can get those vectors back out. So that recipe basically looks like this. It's not a lot of code. It's a very similar trick to what we did before. So we're going to use this ML utils again and convert vector columns from ML. This is exactly what we did before. We give it a data frame with the columns we want to convert. We give it the name of the columns we want to convert. We then coerce the result to an RDD of rows. We know, because hopefully the API is doing what it says, that those rows contain, in this case, one column, and the value in that column is this guy here, an old school vector. So we can do get as vector from column 0, and then we can call that a row matrix. So this is pretty much what we did before. Once we've got the row matrix, we can just do this, compute SVD. And we can say I want 5 singular values or 5 right singular vectors or whatever I want. And then I can extract from the decomposition. So if we compare these, we should have exactly the same data we saw before. To see, does that look about right? It's getting truncated here. Yeah, it looks about right. I mean, that's just the math. I mean, in theory, it'll be exact. Of course, this is a numeric approximation, but it's close enough. So this is just another one of those handy recipes, right? It's not rocket science. It's just like, well, how do I get from A to B using the current APIs? And let's see, the very last thing here, I may actually skip this for time reasons. The very last thing here is like, oh, we've done all this stuff with the data set, let's go build a model. But I'm going to skip this because, one, you can try this on your own. You're welcome to do it. The code is here. And it's like, we're not going to come up with an awesome model. We'll come up with a model that's better than no model, but it's just probably not worth spending a bunch of time. But it is another example you can play with. What I'd rather do, since we only have about 25 minutes before lunch, is do see if we can get somewhere in here with the natural language processing stuff. Let me also look and see if Databricks CE is back up. Doesn't look good. Anybody else have it running? Nice. Okay. Well, the next thing I'll do is I'll over lunch. My prayer is that by the end of lunch we'll have something everybody can use. Sorry? Oh, I will. No, I will. No, I'm just saying. I'm just talking out loud. That over lunch I will see if I can get that running. But yes, yeah, we'll go through. So the demo here is probably also something that you may have seen before or played around with yourself. It's like some sentiment analysis stuff with Amazon data. But we'll use that as an excuse to look at some natural language processing and a couple of other algorithms here. So the data set here, which is I think the one that we queried at the very beginning of the class, is the Amazon review data set. We can pop this thing up on the screen. And what it has is just these two columns. It has a review with a number of stars, a rating with number of stars, and then review with the full text of the review. So a typical task might be, since we have this labeled data, let's see if we can figure out what language patterns correspond to like positive sentiment versus negative sentiment, and maybe we can apply that to something else. That's like be a pretty common task people want to do. So let's go in and take a look. So one thing we might want to do is, well, I can rename rating to label just to kind of give us column names that, column name will work with the default. And then maybe I want to see how many reviews I have with each label. right? So if we do a group by an account, it comes up like this, right? So right away we've got a problem because we have this sort of classic class imbalance thing, which is like, we've got way more positive reviews. If you put 4 and 5 together, they vastly outnumber these guys. So, exactly, yeah. But we've got like kind of a class imbalance version. It's not a single feature so much, but we've got to figure out something to do about that. So what I'm going to do is I'm going to look at maybe oversampling the negative reviews so that the model doesn't get too far off here. And here's how I can do that. I can take this and I can say, let me go and find all of the reviews where the label is less than 4. And then I'm going to do a sampling with replacement at like a 3x oversampling. And what this does is, so the sampling with replacement is really clever. It samples from a Poisson distribution to figure out how many times each record would show up, and that way it can do all of this in one pass. So it's with replacement notionally, but it doesn't actually hit any record more than once. And then I'm going to union those with the original ones. So let's just see if I do that, what does my distribution look like now? Okay, that looks a lot better, right? So now this is, now it's like at least I've got some decent like representation of these guys numerically. And then we can do fun things just to kind of test our intuition. Like we could say, well, if the review contains the word awesome, what does that distribution look like? It's like, okay, well, those are mostly 5-star reviews. And if the review contains the word poor, what does that look like? Well, those are mostly like 1- and 2-star reviews, right? So just kind of reality check here. So that's not super surprising.
So you don't have to be a regex guru to get that information.
Well, not for this stuff. Well, yeah, we're not going to. There are. I mean, if you do want to do regex processing, you can actually do that along with all this stuff. So there's regex. There's a regex function you can run on columns and a regex extractors and stuff. What we're going to do here is we're going to do kind of a counted bag of words approach here. And we'll look at doing assembling a little pipeline to do that. So I'm going to use regexes to split myself up into words. So for each review, I'm actually going to use this helper called regex tokenizer. I'm going to feed the review text in. We're going to put the output into a column called tokens. And this is the pattern for how we're going to split up the words. So in this case, we're saying it's the delimiter. It's like we're saying in between words is one or more non-word character, but you can do it the other way too. So if you want to define what is a token in your appropriate language, you could flip that around. So this is how I'm going to break up into tokens. Then I want to get rid of stop words in this particular case, right? So stop words are words like of and the that in our particular problem are not informative. So a couple things about that. So this stop words remover, I can take a shortcut here because Spark includes a really bad stop word list for English. So if you're doing a quick and dirty demo like this, you can do this without providing your own stop word list. But in real life, you probably want your own list because one, the one that's built in is terrible. Two, it's only for English. So if you're processing anything from other languages, you've got to supply your own stop word list. Also, you may not always want to remove stop words. Depends on what you're doing, right? So it turns out that if you're trying to do things like author attribution or like anomaly detection, the stop words are more useful than the content words. So it's not always that you want to throw them away. In this particular case, though, we do want to throw them away. And then what we're going to do is we need to make,
Will it allow extracting n-gram features in the text?
Sorry, yeah, n-grams. There is an n-gram helper. I'll show you where it lives. So yeah, exactly. If you wanted n-grams, what you can do is if you go under that ML programming guide again to here, it's this guy here. So there's an n-gram processor that you can use. Yeah, and so there's lots of ways to do this. And again, it's like, I'm not pretending this is, and you can also hook this up with like Stanford NLP. Like if you want to get hardcore, you can, like Stanford NLP is like this huge like package for doing NLP with language models and, named entity recognition, all kinds of other fun stuff. So just using like the built-in stuff, let's pretend that this is good data up to here, and then we have to figure out how are we going to come up with word counts. The general problem is that you don't actually want to have a slot for a count for every single word in the language, right? Because even in like the basic usage of English, you might have 50 or 100,000 words. If you include all the technical words, you might have 1 million words, and you probably don't want all those. So there's two main strategies for dealing with that in Spark in terms of support. So one is count vectorizer. So count vectorizer just finds the most frequently occurring words and chops off after a certain amount. So what this is going to do is it's going to say, I want to find the 1,000 most frequent words as long as they occur in at least 200 documents. So I might end up with less. And that's going to be the length of my vector. So this is going to keep more common words. The other way to do it is TF-IDF, or term frequency, inverse document frequency. You've probably come across that before. That's also supported in Spark. It's just as easy to use. The difference is the TF-IDF is going to move more emphasis towards rarer words, because it's going to preserve every word, and some of those rare words are going to collide with more common words. So like if you want something that's weighted more towards like more common words, you probably want count vectorizer. If you want to preserve like really unusual words, then you want to go with the TF-IDF. If you're interested also in like word embeddings, so Spark is not like a big tool on the neural network and like deep learning end of things. We can talk about that a little bit at the end of class. There's maybe some options for that, but it does have a word-to-vec implementation built in. So if you want word embeddings for your terms, I've got a link to that here, and you can also, it's also under here. It's just really easy to use. You just basically tell it, how many dimensions of an embedding you want, and it goes to town. So we'll set up these guys. We're just configuring these pieces. And the last thing I'm going to do here before I go any further is I'm going to remap the labels, basically just because Amazon star ratings are like 1 through 5, and what I really want is 0-based, so I'm just going to move them all. I'm just going to use a little SQL here. So this is a call select expression. So select allows you to select columns. Select expression allows you to select little SQL snippets. So you could do this various ways, but I thought like if you know SQL, you might think of it this way. I want to take label -1 as label. So you can just throw that in there and that will work. So select expression is another handy way to kind of reshape a data frame. So now I've got this thing with 0-based labels. This is my pipeline that has the tokenizer, the stop word remover, and the count vectorizer in it. And then I could fit that against the data and transform and kind of see where I end up. It's not going to be human intelligible, but you can see what's happening. So we've got the original review, we've got the labels, then we've got the tokens, which was the next column. And then this is like super wide, but if I scroll over, the next one should be the one with the stop words removed. So this is the one without the stop words. And then if I keep going, I should eventually get the vector. So here's my vector. This is my vector here. The 0 says that it's stored as sparse vector. 534 is how long it was. So what happened? I said 1,000. Why did I get 534? Probably there were not 1,000 words that occurred in like 200 documents of my sample. It's hard to believe. I'll have to take a look at that. But I've got 534 that are kept. Oh, you know what it is? It's because once we get rid of all the stop words and stuff, I guess the problem is we've chopped out all of those, and so we've kind of modulating that a little bit. And now we've got 534 left. So these are the positions, and then these are the actual counts. So these are like literally the number of times that word occurred. So now we want to do like let's say we want to do some classification on here. We want to do a training test split, but we've got to be careful because since we upsampled part of the data set, if we do a training test split after the upsampling, we're going to end up with data that's the same in the training and the test section, right? So what we need to do is go back to the original data, split that, and then do the upsampling. Does that make sense? Because we want to make sure the training data doesn't have, the test data doesn't have any data that was also in the training set. So the way I'm going to do that is just go back to original data and do random split here. Then I'm going to manually say the training data is the first of the two splits, that is the 0.7 or 70% split. Then I'll do my upsampling trick. I'm also going to mark this for caching just because it may run faster. So what this does, what .cache does, is it says to Spark, don't do anything now, but the first time you evaluate these records, if you have space in memory, keep them. So you don't have to go and reread them off disk or recompute the earlier steps. So I'm going to go do that, and then over here for test, I'll grab the other split. And for test, I'm not going to do the upsampling because it's either right or wrong. Having the record come up more than once shouldn't matter. So we can go ahead and do this. And then I've got train count plus test count. Why did I do that? Well, it's not so much that I'm interested in counting. It's that by doing a count, I'm forcing Spark to evaluate the training data frame, which is going to get it loaded up into memory. And one of the things that, again, we don't have time to do a lot of infrastructure stuff here today, but a useful thing to explore at some point is the Spark UI. So if you go over here to View Spark UI, it'll open up this tab over here. Now, the left-hand nav here is Databricks, but everything from this part over to the right is open source Spark. So if you're running any kind of Spark, even on your local laptop, you have access to the Spark UI. The Spark UI is super awesome because it allows you to tune and troubleshoot all kinds of situations without reading any logs, just by looking at graphs and statistics about the different jobs. So in this case, what I wanted to do was see, well, did that fit in memory? How much memory is it using? If I click here under the Storage tab, I can see information about the memory usage. So that is, that particular data set is fitting in memory 100%. It's only taking up 73 megs of memory. This mess over here will hopefully get fixed in Spark. This is, if you don't give the table a friendly human name, this is actually a compressed version of a tree description of the query plan. I consider it just a bug that hasn't been a high priority to fix yet. So that's what this nonsense is. But this is the data frame that we were talking about. OK, so now I've got some data here. And now I guess I should have started this before I did that demo, since it takes a couple of minutes. So this is a new feature in Spark 2.1 is multi-class logistic regression. So prior to Spark 2.1, there was infrastructure there, but it wasn't quite finished. And now it's there. You just use it as regular old logistic regression. It's just if there's more than one, if there's more, labels aren't just like two values, it automatically does multi-class. And so we're just going to instantiate logistic regression, do a fit, do a transform, pull out the predictions and labels after we've done the prediction. And then we're going to go and see how we did. So in this case, we're going to instantiate a multi-class classification evaluator. So this is a subtype of evaluator like we used before, but this one knows different statistics, right? So the other one, the regression evaluator, knows RMSE, MSE, MA, mean absolute error, and R squared. This guy knows things like class accuracy or F1 score, stuff like that. So see how long this one takes.
So, quick question. These days, which type of algorithms or machine learning tools are people using Spark for and enjoying the most success? Classifications or?
I mean, all of the built-in algorithms, which is not as much of a punt as it sounds like, because it's not that many. There's only like a couple dozen. They all perform really well. Probably the one that is the highest capacity, most powerful model that's implemented in core Spark is the gradient boosted tree. So there's a GBT regressor in Spark, and that's like probably in terms of most expressive, highest capacity model that has really really nice scale out performance on Spark. I would say is probably GBT. We may do one of those, but then simpler ones like this work also.
Just out of curiosity, how many nodes in this cluster you are the one you're showing us?
The one that I'm doing right here, I actually intentionally made it just like the community edition because I felt like otherwise it's kind of cheating. I want to show you results that are similar to what you're going to get if you go home and play around with this. So I spun this up as the same exact thing as on the free version.
Just like in terms of AWS, how much these are like?
It's 0.88 vCores and 6 gigs of RAM. It's one container out of I think 9 on a got to remember which instance type. But we basically, we pack like 9 or 10 of these containers onto a single machine that's got probably 64 gigs of RAM and, yeah, I don't know, maybe 16 cores. I don't know. I'm sure I'm going to get the numbers wrong. I got to go take a look. Plus, every quarter they change the instance types. But it's something. This is just like the free version. Oh, and not every. I take back what I said. There's like like the one model that sort of jumps out as not being so great, or is the multi-layer perceptron. So we can talk more about neural net stuff later. There's a multi-layer perceptron classifier in there. The problem is that the activation in there is sigmoid. If they just change the activation to ReLU, it would be like, for what it is, it would actually be quite nice. But sigmoid is just, you throw all the horsepower in the world at it, it's just going to converge really slow. So don't waste your time. Okay, cool. So we've got this thing here, and we've got a class accuracy of about 50%. Which is not terrible, right? It's significantly better than chance, but it's not great either, right? And the real problem here is that we're trying to discern all these really subtle things, like 1-star versus 2-star based on the vocabulary, or 4-star versus 5-star on the vocabulary. And those are just, there's not a lot of information there, at least not the way we're currently looking at it with our current featureization. So let's look at like a more simple problem, like if we just want positive or negative, then things get easier, and that's also something we might want to sort of more realistically do. So let's take our label and let's just binarize it or threshold it into like good or bad. So what I'm going to do is use the built-in binarizer helper and say the input column for that is going to be label. The output we'll call bucket label. And I'm going to set the threshold at 2.5. So 0, 1, and 2, which were the 1, 2, and 3-star reviews, are bad. 4-star and 5-star reviews are good. And we'll see how that works.
So the threshold 2.5 is the upper limit of what you can.
It's the split in the, so the binarizer is going to spit out zeros and ones.
Okay.
And what this is saying is the value in this column, if it's lower than threshold, becomes 0.
Okay, got it.
Cool. Okay, so now I've got this guy. So what I'm going to do is make a slightly new pipeline. So I'm going to reuse the pieces I had before and just add binarizer onto it. Then I'm going to do, once again, a fit and a transform. I'm going to rename the bucket label column back to label, just because it's easier to do this once than to put bucket label in every other place that I need to put it. Then I'll do my upsampling and training and test trick that I did before, and then we'll spin up a logistic regression here and see how this does. This should be quicker. Cool, so that gets us to about 82% on the accuracy. So that's actually not terrible. Maybe we want to, since we're down to just positive or negative, maybe we want to see things like an ROC curve or something like that. So if we want something like that, what we can do is instantiate a binary classification evaluator. And that's going to actually default to area under ROC curve as its metric. So we can say the area under the curve for this thing is 0.71, and we can plot that. Now this is a Databricks only feature that generates this plot, but it's kind of nice. We can generate an ROC curve and kind of look at different points along here once we've got that guy. If you do an explain params on that, you can see you've got area under curve or area under precision recall for your choices there. So let's see, it's coming right up on lunch, and I don't want to launch into kind of the next thing before and run out of time there. So I'll stop here. I'll hang out if anybody has any questions.